Welcome to the Zero Input Agriculture Podcast. Today we are talking to Julian Gough. Did I pronounce that
Very
correctly?
good.
I got it right?
Gough,
Okay.
yes. Excellent. No one in Germany ever gets it right. I live in Germany and nobody gets it right ever. Yeah. So
Well,
well done.
it's a first. Um, so a lot of the time this is presented as kind of I guess, a fringe or quirky gardening show, and I think I've outdone myself today in bringing a cosmologist, I think you could possibly be classified as.
It's very
Um,
hard to know. Coming in from a sort of philosophical background, definitely
yeah,
not a deep cosmology background, but I've ended up deeply into cosmology. Yeah, yeah. But coming in from the side.
Yeah,
Mhm.
I became aware of Julian's work because I read a book by physicist Lee Smolin, uh,
Yes.
which which started a theory called cosmic natural selection, which is the idea that when you form a black hole out in space, inside that little bubble of reality, a whole new universe gets born, and then it has little babies inside it, etc.,
Mm.
etc., etc., like Russian nesting dolls, but thousands and millions and trillions packed inside. And it was a theory that just resonated with me the second I saw it. But the book itself by Smolin was kind of like the first step, and it left a lot of loose ends.
Yeah.
And
Mm.
Julian's been
I think it's up
extending
now
that
somewhere.
work.
Mm.
Julian's
Mm.
been extending that work in all sorts of amazing directions, which I think are tapping even more deeply into the biological
Mm.
parallels between this theory of cosmology and what we know about biology. And my
Yeah.
listeners know that I'm kind of mad about biology, so this just made perfect sense. And I'm also interested in like history on every possible scale. So I am really, really happy to have Julian here. So I'll throw over to you to tell me a bit more about the winding path that led you
Mm.
to this current point, and maybe even a kind of question at the end. Do you think if you had trained to be a physicist that you never would have ended up with
Oh.
this set of ideas?
Totally. If I'd formally trained inside physics and then astrophysics and then cosmology, I wouldn't have been able to do the pattern recognition I've done that has led me to this point where I am actually able to make successful predictions about the early universe that the
Mm.
James Webb confirms. And
Hmm.
it's completely because I'm coming in from the outside. And this happens, I think, again and again in scientific fields. The they narrow they get narrower and narrower and more specialized, and they get more locked into their paradigm. And their paradigm is excellent for a very long time, and then it runs out of road, and it starts to get a little shaky around the edges. But they're so locked into their paradigm they can't step outside it, and because the usually what's wrong isn't something in the theory. It's a fundamental assumption underlying the theory that isn't examinable because it's not inside the theory.
Yeah.
And I think that's what's happened with cosmology. So I was very lucky to come into it in the very roundabout way that I did, because I was able to bring a lot of perspectives from other fields that I was also interested in to this. I mean, the initial theory you mentioned, Lee Smolin's book, the Life of the Cosmos, which where he lays out the idea of cosmological natural selection that maybe universes evolved. That is I think that's one of the most profound insights of the last 50, 60, 70 years. And it came about because he was a theoretical physicist who, in his spare time, read a lot of evolutionary biology because it was fun. He had no idea that it would be of any use to him in his day-to-day work, where he's working on quantum gravity and trying to unify quantum mechanics and general relativity. And what the hell has evolutionary biology got to do? He just read it to relax and because it was fun.
Do
And he was
academics
reading
have
Lin.
spare time anymore to read like a whole
I
other
don't think they do
field?
anymore.
They're so
I
busy
think it's. I
filling out
think
grant applications
yeah.
that they
Oh my
have no
God.
chance. Yeah.
Their lives are a nightmare. I mean, I talk to a lot of them now because I'm getting more and more into the field. I'm like, their lives are a nightmare. It's all grant applications, it's all paperwork, it's all data analysis. It's all trying to keep up with the papers in your not in your field, but in your the sub fields that you. It's they have no real free thinking time. I think Lee Smolin was one of the last of the. It was before the internet. It was before smartphones. It was before the crazy overpublication of papers, and he was able to have a bit of free time. He probably didn't have kids. I'm guessing that's another factor. and um, and he was reading Lynn Margulis. He was reading Stephen Jay Gould. So he's reading relatively broad popular accounts of evolutionary biology. And he had this fantastic insight, which came from his teacher one of his mentors, John Wheeler, great American physicist, John Wheeler, very, very, very interesting man, because John Wheeler had made the key connection, I think, that led to everything that's happened subsequently, which is he realized we have two uh, mysteries in our universe uh, that have a lot in common. They involve singularities, and a singularity is where mass energy collapses under gravity to a point where the gravity it's so dense and the gravity is so intense that nothing can escape it. Light can't escape it. Nothing can come back from a black hole. And once you've hit that point, it's basically left the universe. Like well, anything that goes into a black hole is not coming. It's not coming back out. And what happens? Where does it? Does it mean anything to say where does it go? Mass energy in our universe, when that happens, we call it a black hole. Stars, when they run out of fuel, they don't have radiative energy pushing back against the gravitational collapse. They run out of fuel, they collapse. The gravity just takes over. And if they're big enough, they get dense enough as they collapse that light can't escape, that nothing can escape, and we don't know what happens because general relativity breaks down, quantum mechanics breaks down, and you get what we call a singularity. A singularity is a point where mathematically, if according to our existing theories, all that mass, like the size of a sun, is now goes to a point with no dimensionality at all. And
Mm.
that probably can't happen,
Yeah. Yeah.
but that's what our math says happens. The math starts spitting out infinities at that point. So we know our theories break down at that point. So we call it a singularity. Okay.
Mm.
There's another singularity in our universe, uh, and it's called the Big Bang.
Mm.
So if you take all the mass energy in our universe, which has been we realized early in the 20th century has been expanding, the galaxies are shooting away from each other for a very long time. You can work out what that very long time is because if they've been shooting away from each other for a very long time, just run the tape backwards. And what is the point where they will meet? They meet in a singularity about 13.8 billion years ago. So our universe appears to have appeared from a point 13.8 billion years ago and expanded dramatically. And in our universe, we have black holes where mass energy disappears to a point and vanishes from our universe. So
Mm.
John Wheeler's big idea was, wait a minute, they look like the same thing from different sides.
Yeah.
What if a black hole in a parent universe collapses down to a point and bounces? But it's outside of the space-time of the parent universe. It's outside the bubble, the membrane of the parent universe now. What if that then starts a new bubble of space-time, which then expands from a Big Bang to form a new universe, a child universe?
Mm.
And it's a really beautiful idea that
Mm.
universes give birth to universes through black holes. There's this painful birth process, and then bam, there's a new baby universe, a new bubble of space-time expanding outside the bubble of space-time of the parent universe. I don't see them as nested dolls, but you can think of them that way. But I mean, it feels like the physics of it is that there's a three dimensions of space and one of time bubble. But when you go down to that singularity, when you collapse out of that, you're just basically budding off. You're budding off a little new bubble of space time that then expands outside the parent universe.
It's
And
almost
that,
like imaginary numbers that you rotate into a whole
mm,
new axis that you didn't realize
yeah,
was there before.
exactly. You're going through the X and the Y and the zero. You're going through that, and you're coming out the other side. Once you go out the other side of it, you're in a completely different,
Set of
transformed
axes.
space time.
Yeah.
Yeah, yeah, yeah. So Wheeler had thought, wonder if what if the qualities of the child universe were just radically different from the parent universe? What if the basic parameters of matter, so things like the mass of the electron, things like the strong nuclear force and the weak nuclear force, the fine structure constant, what if these and there aren't many of them,
Mm.
what if this 20 or 30 little variables that create a universe were just randomly scrambled in the child universe? And he thought, well, then with enough scramblings, you might get a really strange, complicated, and interesting universe like our one,
Mm.
which I don't think is a particularly strong argument. It's kind of the anthropic principle that if there's enough random universes, you might get one that's very life friendly and complicated and interesting by
Mm.
chance.
Mm.
Smolin's breakthrough was he'd read some. Oh, can you swear on this podcast? He'd read some
Swear
evolutionary
away.
biology. He
Swear away.
actually he actually knew something that wasn't just reductionist, materialist, mathematical, formulas.
Mm.
He knew that evolution. He knew the magic of evolution, the magic of Darwinian evolution, the completely scientifically uh, explicable process that leads to these magical outcomes like kangaroos and podcast hosts, over given enough time. Um, and he thought, what if the child universe wasn't randomly different from the parent? What if there was just slight variation? What if it was very like the parent, but with some slight variation? You would get Darwinian evolution.
Mm.
You'd have to get Darwinian evolution. You don't need, it's not like this competition and fighting for resources and any of the more complex stuff that you get with biological. You would just get the simplest, cleanest form of Darwinian evolution. Some universes would have variations that would lead to a child universe. Some black holes would generate a universe with a variation in the basic parameters of matter that would lead to a child universe that would produce more black holes rather than less black holes.
Mm.
And that's going to be a more reproductively successful universe. And now you've moved towards a more reproductively successful universe. Some of its offspring will be less reproductively successful, but some will be more reproductively successful. And so you should get runaway uh, reproductive success of
Mm.
universes. You should get runaway black hole production. You should get, the earliest, most primitive universes might produce one or two black holes.
Mm.
But pretty soon, you're going to end up with universes that produce a hell of a lot of black holes.
And
Because
which is what we see
that's just the
around us.
dynamics. What we see around us, because if you
Yeah.
look at our universe, they did some Italian astronomy group did a survey 2 or 3 years ago where they actually tried to finally count how many black holes exist in our universe. And obviously you can't see them, so it's difficult. You're doing a statistical analysis of how many stars of that size are there, how long do they live, when do they collapse. But there's probably roughly, and they're not going to be out by more, they're not going to be out by an order of magnitude. There's 40 quintillion black holes in our universe. 40
Hmm.
quintillion already, and there's going to be more over time. So we're pretty good at producing black holes. So Lee Smolin wrote a paper, and he published it in the Journal of Classical and Quantum Gravity, where nobody read it except
Hmm.
100 guys who are into classical and quantum gravity and are not into evolution and have not read any Lynn Margulis. And then he eventually wrote a book, The Life of the Cosmos, which is published by Oxford University Press, and it's a great book. You've read it, I've read
Yeah.
it, but has everybody on Earth read it? No, they haven't.
It's still pretty
Um,
obscure.
it's still pretty obscure, and I think it's because there are different reasons for that. But one reason is I think he's a little nervous about introducing his big idea,
Mm.
and he doesn't introduce it for about 100 pages. So I think a lot of people have bailed before they get that far. And
Did he publish it relatively late in life too?
not late in life. I think he published it about 4 years after his initial paper, because
Hmm.
I think the paper got enough attention that someone said, you should do a book on this, commissioned a book. So it got around 95. I think the paper was in 91, 92, or 91, 92, around Christmas. And the book was 95. But again, the paper was published before the internet, so you had to go to a library and pick up a paper copy of the Journal of Classical and Quantum Gravity. If you're interested in biological theories you're not going to look in there.
You're not looking in there, yeah.
So there was huge sociological issues, I think, that meant that it never gained any traction. The people that could have done wonderful work with this theory didn't exist. There were
Mm.
people with a profound understanding of evolutionary biology and of astrophysics and cosmology, and there weren't any. So I think it was, I've said this before, but it was in an information shadow. It was in this terrible information shadow where nobody could see it. Nobody could understand. Nobody really got the implications of it. The implications were not fully understood. Also, he was dealing with the limited information available at the time. In the early 90s, we just didn't know uh, remotely as much as we do now about particularly black holes and supermassive black holes and their relationship, which is
Mm.
where my breakthroughs came. He couldn't have had the breakthroughs I had because he didn't have the data. So we've learned a lot about those things. Yeah, I should let you interrupt me and steer
Oh,
this
no,
because
no,
otherwise
no.
I'm gonna.
Um, well, one thing I would maybe point out is that this seems to be another one of these patterns in paradigm shifts that you can often trace the
Mm,
original idea back to someone who was 10, 20, 100 years too early, but
too
at
early.
least they got
Yeah,
it
yeah,
written down somewhere and it bumped
yeah, yeah,
around
yeah.
until it found the right person. And I also
Mendelian genetics
exactly.
and yeah,
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 a mutation that needs to find the right place for it to really
yeah,
thrive. But the
yeah.
other thing is personality in science communication.
Mm,
that
Mm.
I don't know much about Smolin, but the pattern you often see is that the
Ah,
original thinker wasn't very good at promoting their ideas, or they weren't in a position where they could afford to do
yeah,
it. And
yeah.
you're coming from a different perspective where your science communication
Mm.
skills are probably like in the top 1% if you compare to typical physicists. So I'm just curious at this point, just to get a bit of reflection.
That's
Now that you're
interesting. Yeah.
starting to get traction, do you think that's a factor in your success up to this point?
I think it's a huge factor. I mean, I really love Lee Smolin. Uh, he came up with one of my favorite ideas of all time. It's up there with Darwin. It's up there. You know,
Mm,
it's like it's unbelievable. It's a massive extension of Darwin. Darwin, comes up with this wonderful evolutionary theory, but it stops at the universe level. And and at this point we apply Darwinian evolution to everything. We can see how it applies to cultural
mm,
evolution. We can see how it applies to technological evolution. We can see how it applies to biological evolution. We can see how it applies to everything. Every complex system that is able to self-complexify and maintain its complexity in a membrane over time, we
mm.
say, well, it's obviously Darwin is the explanation. The Darwinian evolution is the explanation for how it got to be that. And we apply that to everything except the bloody meta-organism, membrane bound with a birth date that they're all wrapped up in. We don't
Mm.
apply it to the universe. And to me, that it's astonishing that we don't. It seems like a blindingly obvious thing once it's pointed out. Of course, the universe itself has to be the result of an evolutionary process.
Mm.
But Smolin, the trouble was that was a side quest for him. He really is obsessed with quantum gravity. He has
Mm.
devoted his life to trying to unify, general relativity and quantum dynamics to come up with a theory a quantum dynamical theory that incorporates gravity, which is a noble quest. But he came up with this brilliant idea outside of his day job, so he didn't get institutional support to pursue this. He was
Mm.
getting paid to do a different job,
Would it
and
potentially have
and
damaged
he
his
was.
career if he had really pushed it?
That's a really excellent question. Yes, I think it would, and I think it did. I think it did. If you look at the reaction to it at the time, I'm writing a book about this, right? So
Mm.
I'm exploring the theory, I'm extending the theory, I'm writing a book about the theory. But half of half of what I'm discovering is about sociology. It's not about the science.
Mm.
To understand what happened and to understand what's happening now, you have to understand the sociology of science. So when he put this idea out there, something very interesting happened. He found himself in conflict with the string theory guys who dominated theoretical physics, which was his field. This blindsided him completely. I don't think he understood the dynamics of what was happening.
Mm.
But what was happening was this. The string theory guys had used the anthropic principle, the idea that there's a bunch
Ah.
of
Hmm.
random universes with randomly different qualities, right?
And we can
And
pick
one of
whichever
them,
one we want.
if there's enough of them, one
Mm.
of them will contain life. And it happens to be this one because we can't observe the other ones because by definition, they don't have life to observe them. So you don't need to explain the complexity of this universe. It just happens with enough random universes. John Wheeler's thing, right?
Yeah.
But the string theorists use that to justify string theory because string theory, one of the problems with string theory was they ended up with about 500 billion different forms of string theory. And you couldn't tell which one was which and which one was true. But if you just grab the anthropic principle, you say, well, string theory could be true because if there was 500 billion different string theory universes, one of them might be complex enough to have life, and we happen to be in it.
Mm.
So they were using that, right? But if Smolin's right and universes evolve under a Darwinian rule and they're moving towards more and more reproductive success, more and more black hole production, it blows up the anthropic principle. It also blows up string theory because instead of there being a random number of string theory universes that the string theory guys predict, there aren't a random number of universes and there aren't arbitrary universes. There are specific lines, evolutionary lines of universe, which have been able to successfully reproduce generation by generation over time. So you don't have this infinite multiverse of all the possible universes, which was another theory, Everettian multiverse. A guy called Everett came up with the idea that all the quantum states that collapse, all the possibility states that collapse, will it go this way? Will it go that way? Will it will
It goes
that
everywhere.
they all that it goes every way, and every time there is a a collapse of a probability wave, both options come into existence as new universes. It's a horrible mathematical nightmare vision. But the idea is that every possible universe has happened, and therefore, of course, a universe like us has happened because every possible universe has happened. Um,
Are these theories of anything? I
Smolin,
think they've been called theories
they're,
of anything.
they're theories of anything, yeah, kind of, yeah. They're mathematical. They're the kind of theories you come up with when you're a mathematician.
Mm.
But Smolin's theory is way more frugal because Smolin is saying, no, there isn't an infinite number of universes. There's a very specific evolutionary line of universes and they come from very primitive universes and they get more complex over time because that leads to greater reproductive success of the universe. There's a reason why a universe gets more complex. It's an evolutionary reason. It's much more frugal. So that infinite possibility space just has little branches and twigs of evolutionary lines going through it. And just you see the big conceptual difference there.
Mm, mm.
But it put him in conflict with the string theory guys, and they took him out at the knees. Like like Leonard Susskind, who was a brilliant physicist, but very much a reductionist materialist, full-on maths only physicist.
Mm,
Uh, he got into public debate with Smolin. There's a record of this online at theedge.org, I think. You can still find this argument. And they have
mm.
this argument about basically anthropic principle versus evolutionary universe. And Susskind uh, kind of, oh,
Acquiesces?
Susskind beats Smolin
Yeah.
in the argument, but he
Mm,
does it by cheating, I think. Well, not
mm,
even, he's not consciously cheating. He's not consciously cheating, but he does it by using arguments that are totally mathematical and not evolutionary, and that don't stand up if you actually look at it from an evolutionary point of view.
mm.
Will I give you a bit on that, or is that too much detail?
Oh, that might be digging into a bit too much
Might
for
be
my
digging in too
general
much.
audience, but I have
Yeah.
one. Well, I'm going to throw a lot of interesting, like far out speculative questions because it's how my mind works, and maybe some of
Yeah.
them will be useful. Can you entertain the thought, as with biological evolution, that there's early splits that lead down very different paths that
Mm,
achieve similar
absolutely.
functional solutions, but with different
Yeah.
details? That there might be
Yeah.
like completely different ways of building universes that we can't even get our heads around.
I think that's almost certainly the case. Yeah, definitely. I would say so.
Mm.
Um, as long as they're reproducing
Yeah.
and they're finding a way to do it, that you're going to get radically different lines. You're not going to get an infinite number of them, but you're going to get different ones.
Mm.
Um, yeah,
Anyway,
you're going to get branching.
it's
Yeah.
a dead end
Um,
kind of question, but it's fun to think about. So that's what I'm here
it
to
it
ask the
is. Well,
fun questions.
we're at a local fitness peak. That's
Mm.
because but we are at a local fitness peak. I think one of the interesting things, and one of the things that very much in Smolin's favor, and it's very hard to argue against, is he's arguing that we are in a fine-tuned universe.
Hmm.
If you change if you change the basic parameters of matter, if you change any of them by a lot, or by even by much, the whole fucking thing falls apart. That you don't have you don't even get atoms. You don't get solid matter. If you change the strong nuclear force by much, weak nuclear force, if you change any of the masses of the particles by much, it all kind of falls apart. You had a local fitness peak. We're very fine-tuned, and that's the sort of thing you should get with an evolutionary
And
universe. We
I
should have
think
evolved
I think in his book he was
to a
arguing
local
that
fitness peak.
it's the black hole formation that seems to be the most finely tuned out of all of the phenomenon. It's the one that's most sensitive to
Yeah.
changes.
Yeah, you'll get if you change those things, you'll get less black holes. You'll ultimately get less black holes. Yeah,
Mm, mm.
exactly. Because that's the thing it should be. That's the thing it would be measuring against. Because the unit of selection is the universe, and it means of reproduction is the black hole. Yeah, yeah.
Now,
It's very interesting. Yeah,
now, this is
but
probably a good place to shift on to talking about your blowtorch theory that
oh, okay, yeah,
just again, like it took it to a whole nother level. And
yeah,
you tell this story so beautifully that I want to hear it. I want to hear it live.
yeah.
I'm so privileged to have an opportunity to hear you rip it off the top of your head.
Well, well, I basically, I guess what you want me to do is take it from Smolin's theory to through the other people that have developed it, including me, to where it is now.
Yeah, yeah, yeah,
Okay,
yeah. If you
yeah,
can, give us a
yeah.
guided tour.
We've done a lot of work on it to move it forward. Okay, so Smolin's theory was uh, as I've laid out, but he thought that black holes were just going to be stellar collapse black holes because back in the early 90s, we basically thought all black holes came from stars ending their life and collapsing
Mm,
into black holes if they were large enough. Uh, They had started to notice something interesting back in the 90s, but they'd only noticed a small number of them. They'd started to notice that there were things called supermassive black holes. Supermassive black holes have the mass of maybe millions of stars or even billions of stars, whereas a stellar collapse black hole is just one star that collapses. um, but you would have to put together millions or billions of these stellar collapse black holes to make a supermassive black hole. They were a bewildering object, but there were only half a dozen of them had been found by the time he wrote his work. Um, since then, we've realized that there's a supermassive black hole at the center of every galaxy we've been able to observe closely enough. There seems to be a supermassive black hole at the center of every galaxy that we can get close enough to see how things are moving at the center of it.
Mm.
And that is very, 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 very interesting. And what so the theory developed a little after Smolin. Some because that Smolin doesn't explain why life comes about. It's
Mm.
like life is an accidental side effect of the complexification of the universe that is happening to increase the number of stellar collapsed black holes, stars collapsing to make black holes.
Mm.
Okay, that's okay. But Clement Vidal, John Smart, Louis Crane, and a few other people scattered around the world, different philosophers, mathematicians, different thinkers, thought about this and came up with a development of the theory, cosmological natural selection plus intelligence, which tried to explain intelligent life. And they realized that one of the side effects of generating life in a universe is you create things like us that can make technologies that can manipulate matter. And one of the things you could technically do if you're manipulating matter is you could produce small artificial black holes.
Mm.
It's technically possible. It's very difficult, but it would be technically possible to produce small black holes, maybe the size of Mount Everest in matter, shoved down to the size of a singularity.
Mm.
Um, you'd need unbelievably powerful lasers or something to compress the matter, but it's technically possible.
Mm.
And if anything that's technically possible might happen, that's the rules in this universe. We could, if it's technically possible, we might well explore that possibility space. So they said if life did evolve, it would be conserved because life might make small black holes. I Between us all, we've come up with a more powerful argument for that, uh, which is based on the fact that black holes are the most efficient energy source in our universe. If
Mm.
you drop matter into a black hole, you can get 42% of the energy back out again.
Mm-hmm. Mm-hmm.
But 42% of the mass you put in it
Yeah.
comes back out. You can get it back out. Technically, it's possible to get 42% of it back out as energy, which is shockingly efficient. Like it's way more efficient even than nuclear fusion. Nuclear fusion, you get 0.7% of the mass back
Yeah.
out as energy.
Yeah.
And nuclear fission, it's 0.1%. So that would be the most efficient form of energy production in the whole universe. If intelligent life forms develop and they want to optimize their energy efficiency and their sustainability, if they want to sustain themselves over time, they will end up making small black holes. So there's a kind of an evolutionary logic to why life would be conserved if it ever emerged and would then be refined. The process of producing life in the universe would be refined over time to make it easier to produce life because that makes it easier ultimately to produce a lot of small black holes and therefore a lot of reproductive success for that universe.
Mm.
So just at the unit of selection of the universe, you're gonna optimize for life once it emerges even once. Does that make sense?
Yeah. 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 A
Yeah.
life-bearing universe has a greater potential to produce vastly more tiny technological black holes, which then produces even more offspring universes
Uh,
inside.
yeah, yeah. Each of those little black holes is a little Big Bang universe. It's reproduced the parent universe's parameters of matter. It's DNA. It's with slight variation. Yeah, and one of the because people often ask this question, but don't the universes get smaller and smaller as the black holes get smaller and smaller? They don't, and that's why this model kind of works. We know that the 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 mass energy and the gravitational energy in a universe net out to zero. That
Mm.
essentially our universe is flat. It's like you could make it out of nothing. You
Yeah.
basically go this way and that way, and you end up with a very high positive and very high negative, mass energy and gravitational energy charge that over time will equalize out. And but you can do a lot in that time. You can have your entire universe develop in that time. So you can build universes out of nothing. So a small universe, oh, a small black hole doesn't necessarily generate a small universe. It generates a full-size universe.
I
Yeah.
have one interesting question, which you probably have wrestled with, but I haven't seen anyone
Mm.
put anything concrete down on paper. So forgive me if I'm like pushing too much. But the mechanism by which information plus variation is
Yes.
passed between the generations. And I just
Yeah.
have an intuition that possibly as black holes get smaller, they become more variable relative to their parent.
That's interesting. Okay. There's a lot to think about in that one. I talk to physicists about this one a lot because that's a huge issue. It's like, what is the inheritance mechanism?
Yeah, what's
What
the
is it?
DNA?
What's the variation mechanism? Yeah.
Yeah.
Like, I mean, the analog of DNA is the basic parameters of matter, but what is it that varies them? Like,
Mm.
why aren't they identical? Um,
And I mean,
and that's
black
really,
holes aren't identical. They vary in their mass and their spin and
they
a
vary
few
in their
other
mass.
properties. Yeah.
Yeah.
And
Vary in mass, spin, and
maybe they're
charge.
like umbrella variables that influence the practical variables in each universe.
This is something that is completely up for discussion because, and I'd love if anyone has any interesting ideas on this, throw them in because this is new territory. We haven't really fully explored this. We don't know what the
Mm.
mechanism of reproduction is, but that's fine. We're essentially exactly where Darwin was when he
Yeah.
wrote Origin of Species. He had no idea what the mechanism of
Yeah.
inheritance was. He didn't
Yeah.
know anything about genes. He didn't know anything about DNA. But he didn't need to say this theory still works.
Yeah.
We now will later on we're going to work out what the mechanism of inheritance is. But there clearly is a mechanism of inheritance and a variation, and this is the consequences. So that's where we're at. We're basically in 1860 something on this theory. We do see evidence of evolution.
Mm.
It has huge theoretic. It has huge uh, explanatory power. It has huge
Mm.
predictive power, but we don't know what the mechanisms are. Yeah, yeah, yeah.
Well, for example,
But
this is
if intelligent, sorry, yeah, no,
no, no,
one
go,
more
go,
thing is
go.
occurring to me.
Yeah.
Yeah, you're right. If intelligent life is creating small black holes further down the developmental path of our specific universe, if that's happening in universes in general, if intelligent life produces small black holes, the intelligent life has probably worked out that this theory, so it would know it's generating universes, so that there's essentially a moral imperative to not generate horrible universes, right? So like isn't that interesting? If you know your power plant is going to actually generate an entire universe, surely there's a moral imperative to not make it a horrible one. So can intelligent life manipulate the parameters of the child universe, even though it's not going to engage with it, that Big Bang is happening outside of our space-time. We are getting the benefit from the black hole. Do we have a moral obligation to the universe we're creating? And
It,
I can't see how you can avoid that question.
that's
Ultimately, it's a very odd one. It
that's
puts us
a
in a God
I
relationship
was about to say
to the baby universe.
it's a supernatural level of care and benevolence for
Yeah,
entities which you by definition can never meet and interact with,
yeah,
but you still
yeah,
care about their whole existence.
yeah.
That's God
It's
in a
interesting, isn't it?
teacup.
It's God. This is an evolutionary theory that generates essentially gods.
Mm,
But purely through evolution. Every step is an evolutionary one. I really like this actually because it 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 heals the divide, I think, between science and religion, between the
yeah.
belief that this is a meaningful universe that feels shaped and that where life matters and the scientific thing, but everything is just particles and parameters of matter playing out over time.
Mm,
They're both true in this model. They're
yeah.
both true.
Yeah.
You get a step-by-step way of coming from the simplest possible matter in the simplest possible universe, just directly collapsing into black holes and generating big bangs. And over time, complexifying until you get to something like this. And by the time you've got this far, you've essentially got godlike entities.
Mm,
So
in the mix.
it's an interesting solution to the problem. You can be an absolute total, you know, reductionist materialist scientist who only believes in the empirical evidence of, and you can say, and that approach will give ultimately will give you godlike entities.
Yeah. Yeah, yeah,
Yeah.
yeah.
Very,
Yeah.
very interesting. And we are that godlike entity coming into being in this universe.
Yeah.
It puts us
Yeah.
the other side of God. It's very interesting.
Mm,
We're part of God coming into being. This is a one someone I always quote when if the conversation gets to this kind of point is Teilhard de Chardin, Pierre Teilhard de Chardin. He was a Jesuit paleontologist, absolute believer in Darwinian evolution. He said, evolution explains everything.
mm,
Like he was, which is tricky when you're a Jesuit and your employer is essentially in the Vatican. So, but he was one of the guys who discovered the skull of what was then called Peking man, like early hominids in Asia. He was a great paleontologist, great evolutionary theorist, but he was also a Jesuit. He was a religious believer, and he said this line which I really really like, um, that the universe is God coming into being.
mm,
That the self-complexification of the universe is going somewhere that is essentially godlike. That from where we are right now might as well be God. He coined the idea of the noosphere, the idea that the Earth, and he did this in the 30s. He essentially described the internet and the World Wide Web and the network of satellites that connect us all and social media and exactly what we're doing now. He
mm,
described this in the 30s. He said that the direction of evolution culturally, technologically, biologically, is moving towards all of the minds on Earth being interconnected technologically through a network of stuff exactly like this, exactly how we're communicating now,
mm,
and that will form essentially a single entity, a single mind, which you call the noosphere, the mind sphere, the noosphere. My wife does not like the word noosphere because nobody knows what nous means, because they don't speak as much ancient Greek as they used to. So she says she calls it the thinky sphere, which I think is the better term. So let's call it the thinky sphere. So the Earth he said, will eventually be surrounded by a thinky sphere. The entire globe will be one interconnected mind, and that will have its own thoughts and its own consequences. And I think that's exactly what we're seeing now. You and I
mm,
are having our individual thoughts and we're communicating individually to each other, but we are part of a thinky sphere,
mm.
and we are nodes in a network of minds that has its own energy and has its own force.
Yeah.
Yeah.
And it has a
Yeah.
sense of purpose, even if it's not always consciously apparent every step of the way.
Yeah.
Mm,
Yeah, yeah. And I think it's very like a human mind. There's what we all think we're doing, and there's what we're subconsciously doing. There's a lot of
there's levels to it.
a lot of
Yeah.
the there's levels to it. A lot of the unconscious of humans networks into a sort of networked unconscious actions. It's very, very interesting to think
Mm.
of it that way. Yeah.
I have one question going back a little bit.
Right.
Um, how does the black hole information paradox tie
Mm.
into this theory? That quantum theory says that all particles kind of have this information that can't be destroyed, it just gets
Yeah.
transformed. But when you
Yeah.
create a black hole, it seems to just kind of fall off the edge of the map. Could
Well,
that
the
be,
information
yeah, like what, how much
I don't see
information
I
could
don't see a
transfer through?
problem with that. It feels to me like that there's if the information isn't lost, it's lost to our universe, but it's not
Mm,
lost to the universe of universes because
yeah,
it continues into the child universe. The
yeah.
information is in the child universe. So I think it actually is good for quantum mechanics, that this theory, because this theory gives you somewhere for that information to go. And then you have to, I think you can drag in Noether's theorem. I have a very good physicist friend of mine who's is pretty convinced that Noether's theorem will really help us here,
Mm,
which is she was a great uh, physicist, mathematician
mm,
in the early 20th century. Einstein loved her. Einstein said she was one of the great thinkers, and she was unfairly overlooked. She died young.
mm,
But Noether's theorem is a conservation theorem that says where there's a symmetry, there has to be a conservation.
mm,
And if mass energy leaves our universe and in a black hole and starts off again in a mildly transformed in a Big Bang, you're going to have a symmetry through that should allow conservation of information. So I think you can solve the problem without any woo-woo, without any nonsense. I think it's a solvable problem.
mm.
Yeah, yeah,
And then you've got
yeah.
Hawking radiation on the other side, where the
That's a
information
tricky one.
is
Yeah,
theoretically leaking back out again.
theoretically leaking back out, and black holes are evaporating. I don't know. I'm not
Yeah.
worried about that. I yes,
Mm.
that these are interesting things to
They're,
think
they're
about.
little
What are the
loose threads
consequences?
to pull at
They're
the
loose threads.
edges. Yeah.
I don't think they're fatal to the theory at all. I
Mm,
think I, there's I'd be astounded if this theory was finished now. It isn't. I would be astonished if there weren't weird little details that we pull on them and we find a whole new thing
mm,
opening up. But there are a lot of interesting issues around our current understanding of black holes. Our current understanding of black holes is recent and it's partial and it's fragile. So they will transform again as we dig into it. I should probably actually finish the.
oh yeah.
I've been doing this in a bit of a shaggy dog story way.
Yeah.
I should probably bring in what I brought to the theory and how that's led to some predictive success.
Hmm. Hmm.
Will I do that now? Is that
Yes, yeah,
good
yeah, yeah,
for
yeah.
you?
Keep rolling, keep
Okay,
rolling.
okay.
I
So
want to
that
hear
was
the
a
story
situation.
again.
That was a situation where when I sort of got involved in this was Smolin, basics of the theory, stars collapse, black holes, small black holes, maximize for that. Um, uh, Vidal, Smart, Crane, Wright, and others think life makes sense in this paradigm because life could generate small black holes and be even more reproductively successful. You get a lot more small black holes per unit mass with life transforming asteroids and planets into lots of small black holes than you do just from stellar collapse. So it's a much more efficient breakthrough, so it will be conserved. My breakthrough was when the James Webb was about to come online. When the James Webb Space Telescope, which NASA and the European Space Agency launched in 2022. Did they launch it in 21? It took months to get into position. It's a million miles away from Earth. And it's this beautiful, unbelievable cathedral of a telescope that floats in space a million miles away from Earth, um, with like five heat shields the size of tennis courts keeping the sun off it. And it's super chilled. And it's able, as a result, to see the infrared light from the birth of the universe, from just after, the first billion years after the Big Bang. Light which has been redshifted and stretched by the expansion of the universe till it's right down in the infrared. Um, and it can see it. We could never see this light before. It's a real technological miracle that we've been able to pull out one off. It's because every telescope on Earth is too hot.
Mm, mm,
The air we're looking through is too hot. Like
mm,
everything is hotter than the infrared light from the birth of the universe, which is very dim and very. Yeah. So this is the first time we've ever seen it. So that was about to come online in 2022, and I had become obsessed with the idea of an evolved universe because I'd independently. It's one of those funny things. I'd independently realized the universe had all the hallmarks of an evolved organism. And then after I'd worked this out and been thinking about it for a while, I thought I should Google this. Has anyone else come up with this? I Google away. Discovered Lee Smolin has written a book
mm,
about it 20 years earlier. I was like, oh God damn it. But that's great. At least I'm not, at least that's interesting. A proper scientist has a proper theory about this. That's okay. I was a bit gutted though that I hadn't just thought it up for the first time. And read Smolin stuff. Then I find the other guy's stuff. Read theirs. And then realize there's this natural experiment coming up. The James Webb is going to give us actual information about the first billion years, the key first billion years.
mm,
And there's a set of expectations about that within the current paradigm. But if this theory has any value, if it's a real theory, you should be able to make predictions about the early universe
mm,
that couldn't be made inside the existing paradigm. An evolved universe should be developmentally different to a random one-shot universe
mm.
in the first billion years. So I basically sat down for a week or two and I thought through the implications of this theory from first principles. And this is my big contribution to the field. Um, I realized one of the implications of this theory that I don't think anyone had pointed out before, which is the existence of supermassive black holes
Mm,
in our universe. If we've got a trillion supermassive black holes in our universe, because there's roughly a trillion, probably 2 trillion galaxies, doesn't matter, roughly. We'll say a trillion, it's easier. No one's going to count them tonight and pick me up on it. It's
It,
it's in that area.
is it worth pointing
It's
out too that the conventional theories have a hard time explaining how those supermassive black holes formed? It's very
been a huge
difficult.
problem.
Yeah, if you have stellar mass black holes just colliding with
Yeah.
each other, eventually building it up, it would take like orders of magnitude longer than the age of the universe.
Well, it wouldn't, no, it's not quite the case, but it's what's happened is that Okay, the existing paradigm is, this is a one-shot universe that happens to have come into existence at the Big Bang. It has got no prehistory. That just happened, and that's just. By the way, that is essentially, religious belief. They believe in a moment of creation. Like it's very, the mainstream has become unbelievably religious. Uh, so there's one universe. It happened in a Big Bang for no reason, out of nowhere, and it's the properties of matter in it are arbitrary. They're just random, and it happens to have complexified. Okay. The way they explain that is mostly they use gravity, uh, and that's a problem. So getting the structure formation you see in our universe, where you've got all these galaxies and stars and planets and uh, quite complex structures
Yeah,
becoming quite
tendrils and
fast.
membranes and voids and rings and all of these complex things on
Yeah,
different
you've got quite
scales.
complex. Yeah. To do that, they're basically using gravity. But the trouble is there isn't enough matter visible to do it just using gravity. Just using the random movement of particles under gravity to assemble these structures. So they've added in dark matter. Now, dark matter, you can't see it. You can't
You're not
touch it.
allowed to
You
look at
can't
it.
taste it. You can't smell it. You can't
You're
look at
not
it.
allowed to
No one
look
has
at
been
it.
able to. No one has been able to detect it. They've spent enormous amounts of money on enormous numbers of programs trying to detect a dark matter particle of some kind. They've eliminated lots of possibilities, and they still haven't detected a single dark matter particle. Um, I have previously said that if they were forced to call dark matter angels, until they actually found an actual particle of dark matter, it would make it clearer what's going on here. So you've got the angels of dark matter collapse everything, and the dark matter is where is the dark matter? It's wherever you need it to be to
Yep,
collapse everything.
yep.
So you've got these halos. I love the way that they're also called halos. Isn't that interesting? Halos of dark matter, which you can't see but you have to believe in, float around in the early universe, and they attract matter together, the actual matter we can see,
Mm.
and it stumbles into place under gravity randomly, and you get bits of it accreting, and somehow stars form, but it's a bit hard to form stars because there's no oxygen, there's no carbon, there's no nitrogen, there's none of the elements you need yet because they're made in stars. There's none of those elements you need to cool gas to make it condense to form stars, but nonetheless, somehow stars form. This is the theory that this is what they thought they were going to see in the early universe before the James Webb. And you get clusters of little stars, and then those clusters of little stars maybe start to merge under gravity and nothing else. And the clusters merge with other clusters. And you get about 20 mergers in a row. You will eventually get the beginnings of a galaxy.
Mm.
And now some of the stars are dying and they're forming black holes. And those black holes, some of those black holes merge. It's actually very hard to make them merge mathematically, but okay, well, there must be a way to do it. The last
Add more
parsec that
dark matter.
get add more dark matter, and so the little stellar mass black holes start to merge, and then they merge and they merge, and then they get to be quite big, and then they get bigger, and then the bigger ones merge with other ones, and then they drift into the center of the galaxy, and then eventually you get a supermassive black hole at the center of eventually a galaxy. It's a
Mm.
very slow bottom up uh, process of structure formation.
Mm.
That was the model that they had. This model has become harder and harder to believe in as they've looked further and further back, because as they look further and further back, they keep seeing galaxies, and the
Yeah,
galaxies keep having supermassive black holes at their centers.
from day
It's
one.
and they're running out of time. What was
Mm.
that?
It's from day one. Like the
Yeah.
supermassive black holes seem to form before everything else.
Well, before the James Webb came online, they'd only got a billion years left for all this random stuff to happen, or the random bottom-up structure formation to slowly assemble everything. They were kind of running out of time, but they had a billion years left, and they said, well, technically it's possible, we think, with enough dark matter, and they're using like 5 times more dark matter than there is visible matter in the whole universe. So
Mm.
like but with that, they think they could probably get it all to self-assemble in time, right? And I thought through the logic of an evolved universe that reproduces through black holes and big bangs from first principles, and realized that the supermassive black holes were that supermassive black holes had to be the way the earliest and most primitive universes reproduced, and they
Mm.
had to do it by direct collapse,
Yeah.
right? Direct collapse supermassive black holes. That means that the gas, the matter, had to collapse directly to form the enormous million solar mass black hole in one go.
Yeah, but before the
Without
expansion moved the matter too far away for it to do that.
well, it would have to happen when it was dense. It would happen to happen when it was
Yeah.
early, and it would have to happen when it was smooth. This is a key point.
Mm,
You need an incredibly smooth cloud of gas to get a direct collapse supermassive black hole. Because if it's not smooth, if there's little density differences in it, if there's areas of higher density in it, as it collapses, the areas of higher density will sub-collapse to form stars.
mm.
And once they form stars,
They
they're
push
they're
they
they're
push
out of
all
the
the other
game.
ga they push all the other
They
gas
they they
away.
radiate, they push the gas away and so forth. Yeah,
Yeah.
they blast it away. And they and it so what you need to make a supermassive black hole is an unbelievably smooth amount of an unbelievably large amount of unbelievably smooth gas collapsing without density fluctuations in it.
Mm,
Now, what you see at the very beginning of our universe is an unbelievably smooth gas cloud because we know this from the cosmic microwave background radiation. We've detected the cosmic microwave background, which is essentially the wave of first light that came out shortly after the Big Bang, about 300,000 years after the Big Bang, very close to the Big Bang,
mm,
300,000 years, as matter sort of condensed out of the really hot kind of gluon soup of the early universe, where it was too hot even for matter to form. It was just still the particles that will make up matter when they cool down a bit. But at 330,000 years after the Big Bang, they cool down enough that matter separates out from light. And all those photons of light that have been just sort of trapped inside this gluon, plasma hot soup,
mm,
all these photons are suddenly released at once. So you get this fantastic wave of light, like half the photon, I think more than half the photons in the entire universe. Photons are the little carriers of light that hit your
mm,
eye and you can see things,
mm,
bounce off stuff, massless particle, massless, you know, waves of energy. Half the photons in the entire universe today come from that one flash.
mhm,
And
mhm,
that's we now that of course has been stretched and stretched and stretched by the expansion of the universe till it's into the microwave regime. It's gone way out of visible light down into the microwave. And we picked it up in the whatever 60s, 70s as this cosmic microwave background radiation. It's this fizz, it's this hum. You can pick it up on some radios
mm,
that fills the entire universe. Wherever you point your antenna, you're going to get this fizz because it's from the Big Bang.
mm,
Now, we've analyzed that and analyzed that and analyzed that. We've got a very clear picture now of the cosmic microwave background radiation. It's really, really, really smooth. Very, very, very smooth. And it's not optimized for star formation. But I think it's optimized for black hole, supermassive black hole production. It's
mm,
smooth enough that you can get huge areas to collapse directly. Now, it has, I shouldn't go into all the details, but there's an interesting parallel relationship between the number and size of supermassive black holes. Some are much bigger than others, and the number and size of the very, 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 very slight density fluctuations you get in the cosmic microwave background. They're like fluctuations of like 1 in 10,000, very, very small.
mm,
But they map really closely onto the number and size of the supermassive black holes you've ended up with. So there's interesting circumstantial evidence for that. So I predicted that the way primitive early universes reproduce would have to be through direct collapse supermassive black holes.
mm,
If we have supermassive black holes in our universe, and we do at the center of every galaxy, the way they were produced would be conserved by evolution. You're not going to come up with a much more complicated way of assembling supermassive black holes from millions of separate, complex end-of-life star collapses. That's a
mm.
complicated way to do it. Why would you do that? You would conserve the initial way it happened, which would have to be just direct collapse, because the early universes would be like prokaryotic bacteria.
Yeah.
They would reproduce and nothing else.
It was the
And if you reproduce
first
and nothing
best
else,
solution. It was the first best,
first best
simplest
solution.
solution. Yeah.
Yeah. And it's going to be conserved.
Mm,
But in our universe, instead of all the gas, all the mass, all the early matter collapsing to form a small number of supermassive black holes, a small percentage of our mass energy collapses to form this wave of early direct collapse supermassive black holes. Because we know that the amount that's in these supermassive black holes is not a huge percentage of the mass in the universe. It's relatively small, but it's
mm,
unbelievably significant because
mm,
my argument my argument was that what you will get a wave, like a phase change as the universe expands of direct collapse, supermassive black hole formation. And then it's the supermassive black holes that optimize the conditions for star formation. Because when you get a supermassive black hole, it then attracts gas, plasma, uh, towards itself. That plasma forms an incredibly hot donut of blazing plasma around it. As it falls in, angular momentum is conserved, so it goes faster and faster, and you end up with this hot donut of near light speed gas plasma rotating around a supermassive black hole that itself is rotating at close to the speed of light. You get a dynamo like you would not believe because all of that plasma is charged.
Mm.
So this colossal dynamo then generates, and we know this from looking at how supermassive black holes behave in the more recent universe, which we can observe more clearly. They generate these jets, these radiative jets. So the donut produces this dynamo, and then that produces a massive magnetic field. And at the poles of the magnetic field, particles are shot out north and south, and you get these tremendous jets shooting out of the supermassive black hole. We know this happens because we see it in the more recent years. I'm saying it happens much, much, much earlier and in much, much greater quantities than the mainstream would predict. I'm saying the supermassive black holes come first. They're
Mm.
conserved by evolution. They're the form of reproduction that the prokaryotic universes
Figured out
had
first. Yeah.
figured out first, and they will form first. And once they form, they then shock the surrounding gas with these jets. The shock waves, the pressure waves, create density fluctuations, which shock out star formation around the supermassive black hole. So you should get rapid early star formation around an incredibly early supermassive black hole. So that was the main prediction I made at the time from before the James Webb gave back its data. And for the last 2.5 years, the James Webb has been consistently showing us uh, earlier and earlier compact, bright, mature galaxies around much larger supermassive black holes than they can explain or predict.
Yeah. Yeah.
I was basically right.
Yeah.
So yeah, so that was my big contribution. Because I because these predictions were actually so successful, I've ended up getting funding for further research on this from Emergent Ventures, which is a program run by an economist called Tyler Cowen,
Hmm.
and O'Shaughnessy Ventures funded me as well by Jim O'Shaughnessy is the guy behind that. He's a guy who's they both basically fund innovative ideas, that kind of moonshot ideas that
Yeah.
might
Yeah.
or might not be right, but if they are right, they're really important. So that's where I'm at.
I
And
have,
then blowtorch theory is an expansion of that. Yeah.
yeah. Yeah. I have a related question before we move on.
Mm.
So again, I love playing at the edges of this theory, and I know you're being sensible and focusing on the core, but indulge me.
Yeah.
What happens if you have a black hole merger? If you're
Ooh,
inside one of
yeah.
these new daughter universes and it merges with another universe,
Yeah.
how does that play out? Could that be
I don't
related?
know.
Well,
Yeah.
some of the
But yeah,
models
it's
of the
interesting.
some of the
Yeah.
models of the Big Bang have an early period of inflation that they can't
Yeah. Yeah.
explain. There's like a sudden
Yeah.
expansion in the rate of, sorry, there's a sudden acceleration in the rate of expansion in a relatively brief period of time. And I
Extremely
wondered if
brief. Yeah.
that could be a consequence of a black hole merger in our universe's early development at just the right time. And following on from that,
Yeah.
if I
Yeah.
believe in the cosmic microwave background radiation, there's an inexplicable subtle polarity that one
Mm,
side of the universe looks just a little bit consistently warmer than the other.
mm,
And could that also be evidence of
mm.
a black hole merger?
Okay. Uh, I don't think you need a black hole merger to explain that the universe expanded really, really fast. I don't think it help. I don't think it, I do think it's an interesting question. What
Mm,
happens if two black holes merge, given that universe, if they both generated a universe, what's happening? What's going to happen there? I don't know the answer to that one. I don't know. But I do find the polarity you're talking about in the cosmic microwave background, that's an interesting one. And it ties in with something that happened only last month that you might not even know about,
mm,
which is a really interesting discovery. Lior Shamir, he's a very good mathematician in the States. He's just published a fascinating paper where he went into the all the information we now have about these extremely early galaxies and he worked out their spin direction, right?
Mm.
because galaxies spin, spiral galaxies spin. So what is their spin direction? Is there a pattern in it? Now, obviously, it's arbitrary. Which way up are we? I don't know. So you just basically take our galaxy, say that, let's call that flat.
Hmm.
Which ones are rotating clockwise and which ones are rotating anti-clockwise relative to our one, right? You just need a random
Yeah,
baseline.
just a baseline. Yeah.
There's a huge polarity. Like the two-thirds of them rotate one way and only a third of them rotate the other way. There's a huge preferred direction of rotation in the early universe, in the galaxies. There shouldn't be if it's a random universe.
Mm.
There
Mm.
shouldn't be. So, what is the most obvious explanation for why our universe would be born spinning?
Because the black hole was
Even
spinning.
Shamir says
Yeah.
it's inside a black hole. If
Yeah.
if you're born from a black hole, you're born spinning.
Yeah.
The angular momentum of the mass energy in the previous universe is conserved as it shrinks down,
Mm.
and it's born with spin. So there's strong evidence that our universe was born with spin, and that would also explain why there might be a warmer and cooler side to the cosmic microwave background because if there's spin in that background, some of it's spinning towards you and some of it's spinning away from you. Some of it's red shifted away from you and some of it's blue shifted towards you. There
Is that
could
because our
be
visible universe isn't the entire universe? We're only sampling a subset of that larger spinning structure?
uh yeah, I mean what you're seeing with the cosmic microwave background is kind of a snapshot of the whole thing
Hmm.
back that early. I don't know that I don't know how that would play out. I don't
Hmm.
know what difference
Okay.
that would make. But I do know that we're starting to get more and more evidence that our universe was born spinning, which is a very, very interesting indication that it could have been born out of a black hole.
Mm. What about the impact of ongoing, steady, slow accretion of extra matter into a black hole? Could
I'm
something like
fascinated by
that,
that, and I don't know.
could that be
Yeah.
powering the dark energy idea that the acceleration seems to be speeding up? The things are moving away from each
Yeah.
other. I think I've seen some of those mathematical models that it's as if space-time and matter kind of swap positions when you go from
Hmm.
one universe to a daughter universe, that there's this kind of potential mathematical inversion. So if you're adding
Right.
matter
Yeah.
to one universe, you're adding space time to the daughter universe.
Yeah. I mean, I think that is something that I'm fascinated by what happened. What's the relationship between the parent universe's black hole and its ongoing development
Mm,
and the daughter, the child universe in the Big Bang.
mm,
What's the temporal relation? I'm really fascinated by that, and I don't have a good answer.
yeah,
Like the idea that matter continuing to infall into the black hole after the formation of the baby universe, continues the expansion of the space-time of the baby universe is really, really attractive and interesting, but I don't know if it's true. I
yeah.
emailed Lee Smolin about this because that occurred to me a couple of years ago, and I was like, wait a minute, would increasing infall, ongoing infall of matter, would that continue to expand the child
Mm.
universe? And I asked Lee Smolin what his thoughts on that were, and he didn't answer me. I think he's a bit embarrassed by people like me who kind of like have got really, really enthusiastic about his theory
Mm.
and have like pushed it further than I think he's comfortable going. Like I know he has said that he doesn't like the idea that life might generate technological black holes, and that's a part of
It's a level
the
beyond which
reproductive
he's
cycle of the
comfortable
universe.
with.
He
Yeah.
says it's very science fictional. He doesn't like it. No, he's actually at this point his theory is like a terrifying embarrassment to him, I think.
He could
But I
it
think he's
be that
wrong. I think he's
he didn't anticipate that his theory would itself evolve?
yeah, he didn't anticipate it would evolve. Yeah. Um, but no, no, these oh man, I really wish. I think Lee got shamed out of pursuing his own theory by the mainstream
Hmm.
because it was seen as flaky and it was seen as weird and it was seen as not proper science and it was seen as not properly falsifiable and stuff like that. And it's not true. Like
Mm.
this is a theory that makes falsifiable predictions. He didn't realize that at the time. He made like maybe two predictions. He had a very I don't want to, this sounds negative about him. He came up with a brilliant idea, but he didn't see the full implications of his own idea for understandable reasons that are partly to do with the available data at the time, partly to do with the paradigm that he was trained into and was working under,
Mm,
and partly to do with the fact that there are very useful troves of data and information from outside his field that he just wasn't aware of. I think
yeah, yeah,
there's a lot of systems theory stuff that you can use. There's a lot of evolutionary biology stuff that you can use to develop his theory that he just didn't have available to him, and he didn't at
yeah.
the time. And he went back to his job, his
His
day job,
love.
doing
Yeah.
quantum
I,
gravity.
I,
Yeah,
I have
yeah,
one really fun, well, another really
yeah.
fun question, and this is slightly self-indulgent because it's something I'm wanting to incorporate into my science fiction story that I've written, which
Mm.
has cosmic natural selection as the religion
Right.
of a future civilization, coincidentally.
Very possible.
Um, so
It's a very possible
here's
basis
the
for religion. Yeah.
here's the thought experiment that I want to. It's the end of the series that I haven't written yet, but the first half is
Mm.
done. Um, so if you take a complex object and you move it into a black hole, it gets
Mm.
destroyed. It gets spaghettified along the way.
Spaghettified, yeah.
But
Unless it's a big enough black hole.
yeah,
But yeah, yeah, yeah.
um,
But eventually,
but
yeah, once you get towards the singularity, you're gonna get spaghettified. Yeah, yeah,
so what would happen if you took a complex object like a life form and
yeah.
from all sorts of different directions, a black hole's worth of mass approached it gradually so that there was no traumatic gravitational kind of tidal forces on it, that it just snapped
Oh
its
wow.
finger and was instantly in the interior of a new universe.
Wait, I'm trying to do, oh my God, I'm trying to do the maths on this in my head. And I'm not a maths guy. So you bring the mass energy closer and closer to him, and he's in the center of what's going to be
Symmetrically,
a black hole when they
yeah,
get close enough.
symmetrically from all different directions so that
Oh,
the
maybe.
gravitational forces.
Yeah.
I mean,
Yeah,
wouldn't
it might
time
work.
slow down if
God
you
damn it.
believe relativity as the gravitational?
As the mass as you're at the bottom of a deeper and deeper gravitational well, time slows down relative to an observer outside that well. Yeah, yeah.
Yeah. Does that give a
Hmm.
hint about how you could be on different timelines in different generations of black holes?
Yeah, yeah. It's the effects on time of black holes are very, very extreme, very interesting. Yeah,
Mm,
yeah. The thing is, if you've got a big enough black hole, it's okay. You can cross the Schwarzschild radius and you won't even notice but it has to be really, really big.
yeah.
One of the interesting things about our universe is we happen to be we happen to have the diameter of a black hole of our mass. Like
Hmm.
black holes, the horizons of black holes get very, very big when the mass gets high enough,
Yeah. Yeah.
right? Like the density of matter inside a pretty decent sized, you know, black hole can be the same as water. Like
Mm,
it's
mm,
just like if you had water out to Neptune, that's a black hole.
yeah. Yeah.
It doesn't need to be any denser. The trouble is it collapses in and it does become denser. But the average inside the Schwarzschild radius is not actually doesn't have to be that high.
Mm,
In as and the bigger the black hole gets, the more the mass, then the larger the Schwarzschild radius, the event horizon, the point where you can't come back.
yeah.
And you can so on a small black hole, you're going to get ripped to bits. Like the tidal forces between your feet and your head are just going to pull you into spaghetti
Yeah.
in a small black hole
But if you could make a
as you
really
get
big one
closer to it.
symmetrically, and
Really, really big one. The tidal forces are quite mild, quite
this is
mild.
what I want to make the
And the
finale of
universe
my
is a really, really big one.
well, this is what I want to make the end of my sci-fi theory is that
Yeah.
the finale is that complex life is basically put intact into the very start of the
Oh, that's nice.
next universe, so it has all of those extra billions of years to evolve.
That's nice. That's very sweet.
Mm,
Yeah, I like that. Yeah, yeah, yeah. It
mm,
might be doable.
mm,
Yeah, having it as a symmetrical, big enough mass, symmetrical enough, you might be able to do that.
mm, mm. Anyway,
Yeah.
I'll leave the details of that for the book when I
But you'd
get
be
around to
very
writing
lonely
it.
for a very long time. Like it would take a long time for the for everything around you to turn into anything interesting. Yeah.
Mm,
But
mm.
you'd be there. Maybe you could speed it up, accelerate it.
Yeah,
Yeah.
yeah, yeah, yeah. Anyway, so let me think. What else is on my list of questions? They're all of the scientific ones that I wanted to look at. I wanted to spend a bit of time talking more about the cultural and sociological implications of all of this. And
Oh
probably
yeah,
like
yeah,
the
yeah. Oh,
first
wait, before we
oh
do
oh
that,
yeah,
I've
before
just
we move
realized
on, yeah.
I haven't actually finished the blowtorch theory bit.
Oh, yes,
Give me
yes,
two
yes.
minutes.
Okay, of
Because
course,
I
of
was walking you
course.
through the kind of the development of the theory and how it. So, okay,
Yes.
what we've got
Okay.
now is what we've got now is a universe where there's a wave of supermassive black holes, very
Hmm.
big. They generate the conditions for stars. There's a wave then of stellar collapsed black holes, many orders of magnitude more than their in number than the supermassive, because there's for one supermassive black hole you have a whole galaxy of stars.
Hmm.
Then the stars generate life, and life generates the technologically produced black holes, which again are orders of magnitude more numerous than the stellar black holes. So for one star, which will eventually turn into a black hole, you have planets and moons with these guys producing huge numbers of tiny technologically produced black holes for energy production. So that's your three stages of black hole production in a universe on along our evolutionary line. That's what our universes do.
Mm.
And you will notice that the periodic table, you need more and more of the periodic table to do these three stages.
Yeah.
The first, the direct collapse black holes, don't need much at all. I should, by the way, I don't want to take glory from some people here. Priya Natarajan, Avi Loeb, Volker Brom, a few other really cool people. Martin Rees, I think, was involved in this. Came up with the idea of direct collapse supermassive black holes 18 or 20 years ago. So we know it's mathematically possible to have direct collapse supermassive black holes. In their model, they're tricky to make and they happen after star formation, and stars need to help cool the gas to have the supermassive black. They have a slightly complex model. I've got a really simple model happening earlier.
Mm.
But they did a lot of the work on the mathematics of direct collapse supermassive black holes.
Mm.
It's not a fanciful notion. We know that they are possible. Okay, but so but you only need the most primitive matter. You just need protons, electrons to collapse at the direct collapse supermassive black hole, because that's conserved from a primitive era where there was no complex elements.
Yeah.
To make stars, however, you need slightly more complex. Uh, it's slightly more complicated. You fuse hydrogen, make helium, and so on. As stars play out now, they need carbon, nitrogen, and oxygen, which they generate themselves. But you need carbon, nitrogen, and oxygen to cool gas clouds and to do more efficient fusion. The carbon, nitrogen, oxygen, the CNO cycle of fusion inside stars
Yeah.
is done by carbon, nitrogen, oxygen. Look at what life is made out of. What is life based around? Carbon,
Carbon,
nitrogen,
nitrogen,
oxygen.
oxygen. Yes.
So what you've got there is a classic example of exaptation. You have a
Mm.
classic example of taking something that was developed for one role by evolution, CNO cycle of fusion in stars, and it also helps cool the gas to collapse more efficient stars, smaller, more efficient stars.
Mm.
Uh, Carbon, nitrogen, oxygen are developed just by evolution, by the random exploration of the possibility space of the parameters of matter. They make stars more efficient, they make more black holes. Great. You've got carbon, nitrogen, oxygen, and they are the basis then for biological life. It's exapted from something that's already there. So you don't have to have this huge leap into super complexity of life from
Yeah.
nothing. You can see the evolutionary history of our universe in the development of our single universe.
Mm.
Anyway, I
And
just wanted to
and
throw that one in.
and then the final stage is if we get, as living organisms, we get good at making more heavier elements. They're really useful for all sorts of technological applications, which might eventually lead to artificial black holes.
To us making artificial black holes. So
Yeah.
yeah, the way I've phrased this a lot to stick it in people's heads so they'll stick it on t-shirts is the biology is the first half of the periodic table coming to life. Technology is the second half of the periodic table coming to life.
Mm.
You can see how the technological elements are kind of stacked into the later part of the periodic table. They developed later. They evolved later. They
Mm.
evolved later.
Mm.
They developed later in our universe, and because they evolved later in the history of universes that we are descended from. And you can see the patterns constantly scream evolution at you. They
Mm.
scream evolution at you. A universe is a membrane-bound organism undergoing a developmental path that is highly directional
Mm.
and is aimed at reproductive success. But there's three stages of
Phases. Yeah.
reproductive
Yeah.
success, each of which evolved at a different era, and each of which required more complex elements in order to pull off its full
Now,
development.
is it possible that other life forms are already further along this path of generating artificial black
Sure.
holes? And would they be detectable from Earth if we were, training
Yeah, it's a
the
great
James
question.
Webb in the right direction? What would we be looking for?
Yeah, we're going back to the Fermi paradox. Like, where are they? Where are the? If life is common in the universe, where is it? Because one of my predictions is there's going to be life all over the universe.
Mm,
Now, the thing is, life. I think people get naive about this. They don't realize it takes time to get to the point where life can happen.
mm,
So, the first wave of stars can't produce life. It's not
mm.
going to happen because they haven't produced enough elements yet,
To
because
make
the elements are
planets.
produced in the stars
Yeah,
to produce the planets, to produce the life forms, right?
yeah.
So there's to get to us, you and me talking to each other inside our specific universe, there has to be 3 or 4 rounds of star formation. The first stars make a bunch of elements by fusion, have to distribute them back out to make the next round of stars. So supernova explosions are extremely efficient dispersers of the elements that they've fused at the core. Because this is a problem. Look how evolution solves all these problems. It's so elegant.
Mm,
You are generating the elements you need for the next developmental stage, but you're developing them at the bottom of a gravity well that's 30 times deeper than Earth's.
mm.
Are stars have deep gravity wells. How do you distribute the elements you've made so that they can be used? You need a very efficient kind of explosion. The strong nuclear force, as a star runs out of fuel and collapses, the strong nuclear force, which has held the nuclei together brilliantly for the entire lifetime of the star, as they compress enough, the strong nuclear force flips and becomes repulsive rather than attractive and blows the star up an absolutely staggering efficiency that distributes out those elements into the surrounding interstellar cloud, interstellar medium, which is mostly hydrogen gas. That hydrogen gas is then able to cool, partly because it now has carbon, nitrogen, and oxygen in it, which help it to cool. They soak up photons, drop the temperature, help it condense. So the hydrogen gas is enriched by the explosion from the supernova with the elements it needs to form the next round of stars. They fuse the elements that they've inherited from the previous universe, or sorry, what am I, sorry,
Previous
the
generation of stars.
previous
Yeah.
generation of stars inside this specific universe. The previous generation of stars, uh, they generate even more complex elements and then explode, distribute them, and you get a third round. By the third round of star formation, there's enough elements left in the cloud of gas around the star to form planets
Mm.
and form ultimately life forms. But you have to have several rounds of star formation inside our universe to get to the point where you've got enough material. So it's a superb system, but you have to see it as a system, as a complex, evolved system with really finely tuned parameters of matter that allow for this unbelievable complexification to occur.
I was going to ask, has
And then once
anyone?
you've got
Oh,
your
sorry.
planet, it takes a long time. Sorry, but then
Yeah,
once you've got your planet, what you then have is mineral complexification.
yeah,
Because I just want to get this because your listeners are into
yeah,
evolution. They're
yeah, yeah,
going
yeah,
to
yeah,
love
yeah,
this is really interesting stuff.
yeah.
When you form a planet, you form it from a cloud of material that has the right elements in it for producing us, but it doesn't have the right minerals yet, right? The elements haven't combined into anything complicated yet. There's only about 16 minerals 15, 16, whatever, minerals in the cloud of dust and gas that condenses to form a planet like Earth.
Mm.
You start with 16 minerals. There's 5,500 different minerals, at least on Earth now. So there's been a complexification at the mineral level as the elements react with each other. And there's a chemical logic to that. It's not blind and random.
Mm.
You get a really iron heavy version of the oceans. The oceans on Earth were green
Mm. Green
for
with
a long
iron.
time
Yeah, green with
with
iron.
iron.
Yeah.
Yeah, green with iron. And then you get chemical processes that essentially strip out all the iron. The iron reacts with oxygen as free oxygen gets produced, drops to the bottom. So you get all these layers and layers and layers, which you see in places like Australia and that exposed of iron-rich rock that was sedimentary rock at the bottom of oceans 3, 4 billion years ago. And that iron strips out, and you run through a sulfur-driven early primitive forms of life and you end up with then you get and so it's all with that. It doesn't need free oxygen for a long, long time. Then you get life forms that produce free oxygen, wipe out the previous generations of life, shove them down to the bottom of the sea and into the mud and
Mm.
into anaerobic environments, and then the oxygen transforms the environment massively. Like the most half the minerals on Earth come from life.
Mm.
They don't just come from but So you have to, but to get to that, you need to complexify the minerals. So the minerals are developing the complexity required to allow the conditions to form so that life can then take over and drive the complexification of the mineral environment to suit life.
Mm.
So it's a completely integrated process. It's a completely integrated process. It's exactly what you'd expect from a beautifully evolved Darwinian universe.
Mm. I was going to ask, has anyone investigated how finely tuned the physical parameters are for supernova
Mm.
generation? That's
Oh
probably
God,
still on the
yeah.
to-do list.
Yeah, I don't know. I'm sure the thing is, I'm sure somebody has written interesting papers on how the strong nuclear force flips to allow the explosive energy of that, but they're not thinking of it in terms of
Evolution or fine-tuning,
optimizing
yeah.
for a function
Mm,
because they don't think it has a function. They think
mm,
the stars blow up, they blow up a lot more than they should blow up. Why does that happen? Oh, the strong nuclear force appears to become repulsive at this density. How interesting. But they don't think, wow, that's a great evolutionary trick to get elements to be distributed from the bottom of an extremely deep gravity well into an interstellar medium where they can then form another round of stars. We see it's happening, but the current paradigm doesn't allow you to say that is a function.
yeah, of the whole.
Yeah. So one interesting meta heuristic you can use to look at the universe, right, using my approach, which is Lee Smolin's approach, which is Vidal's approach, which is, there's a lot of people. I, I don't want to take, I don't want to hold credit here, but is to say any extremely peculiar quirk of physics is probably best explained in the downstream consequences for the reproductive success of the universe.
Mm,
And that again and again works. Again and again, if you look at the weird quirks of the physics in our universe that are not explicable in terms of a random one-shot universe, why the hell does it do that? You look for the downstream consequences as the universe develops, and you see that they are increased reproductive success, more black holes, more
mm.
life, and thus also more black holes. So a gorgeous example is that there's no stable nuclei with either 5 or 8 nucleons. Nucleons are
Protons and
protons and
neutrons.
neutrons.
Yeah.
Protons and neutrons. You can mix, it could be a mixture of protons and neutrons. You're not going to get a stable nucleus that has 5 protons and neutrons or 8. That's a weird island of instability because you have to go right up to things like uranium before they become unstable again. Nuclei become unstable. You have to, you know, why the hell are 5 and 8, which are really small atoms, right? Why can't you have 3 neutrons and 2 protons, or 3 protons and 2 neutrons, or why can't you have? That's all. The reason for that, the consequence of that, and then the consequence of that is in the very early universe, after the Big Bang, when you've got hydrogen atoms, which are 1 proton, they don't even need a neutron because there's no second proton to keep them apart, 1 proton, and you've got helium, which is 2 protons and 2 neutrons, because now you need to keep the protons apart, or so the neutrons stop them from pushing each other apart.
Mm,
So you've got that's 4 nucleons. That's 1 nucleon. That's what you've got as the universe blows up after the Big Bang. You've only got protons, but hydrogen nuclei and
helium.
2 neutrons, 2 protons, helium nuclei. If they could fuse to form something stable, you would get, and if two heliums could fuse, 4 and 4 could fuse, you'd get runaway fusion. You'd get the
Yeah.
production of element after element after element after element, and you would fuck up the smooth hydrogen you need to go through all the developmental stages I've just described, to make the stars that are required to drive the production of the elements, and the slow step-by-step process that leads to stable stars, stable planets, stable life, biospheres,
Yeah.
right?
Yeah.
You would get a chaotic runaway mush
Hmm.
if you had a stable 5 or a stable 8. So you don't. So you don't. And that's exactly the kind of mutation, the kind of oddity that will be massively conserved by evolution,
Yeah.
but is
Yeah.
inexplicable in a random arbitrary universe framework. Why does that happen? I don't know.
I just
It's
have to say,
very,
I can't get the image out of my head now. Anytime I think of supernovas, I'm going to see them as
yeah.
like a puffball fungus. A
It's a
cosmic,
puffball fungus.
yeah.
It's yeah, it's solved it in a, it's like what's the yeah, it's like that protein, what's it? That protein that fleas use for the explosive like
Oh, elastin.
Riletin? Elastin? Okay,
No, no,
okay.
no, that's in
Wait,
humans.
no, it's
No, what,
Ritalin, Ritalin. That's a
Resolin.
Resolin.
Resilient, yeah.
It's like something like Resolin. Like it's like why does Resolin exist? It exists because these guys really need to explosively release some energy, like because it's good for their reproductive success. That's why it exists.
Mm.
Evolution made it exist. It's the same for the why is the strong nuclear force flip into a repulsive force at that specific density? Because that maximizes the distribution of the elements, which aids the reproductive success. It's good, isn't it?
Now,
This is a transformative way of thinking about the universe. It's such fun. It's
that
such fun.
well, that gets us back to talking about the cultural and sociological like
Oh yeah,
context and implications of this, because
yeah,
like Enlightenment science has done its darndest for the last 2 centuries to stamp out
yeah.
any mumbling about purpose or
Yeah, yeah,
intention
yeah, yeah, yeah,
anywhere
yeah, yeah,
in reality.
yeah,
And that
yeah,
mindset has yielded a lot of interesting results,
yeah,
and it's helped
yeah,
us shake off a lot of cultural habits
yeah,
that came
yeah, yeah.
beforehand.
Many, many positives to it. Yeah,
But perhaps it's served its purpose, and purpose
yeah.
itself is allowed back into science at the highest levels.
That's something I love about this theory. We get to keep re, reductionist materialism. We get to keep all the tools of science. We get to
Mm,
keep everything we've got. We get to keep all the data we've uncovered, right? We get to keep all of it. But we add something extra that we really need and that will help us to integrate all that we've learned and all of that data into something that actually means something. Because I think it's killing us at the moment. It's killing us that we have learned so much and extracted so little meaning from it.
mhm.
It's psychologically devastating to humanity to be living under a paradigm that says it cannot mean anything. When we know, we continually intuit that it must mean something.
Yeah.
And so you end up with this artificial divide between fundamentalist religions who say we completely understand what it all means and it's all in this book, and
Straight from the mind
fundamentalist
of God.
scientists
Yeah.
who say it means nothing, it cannot mean anything, it's described by this formula. And they're in this fundamentalist standoff, and they're both wrong and they're both right.
Mm.
They both have really valuable insights to share with each other, but they can't because they're just shouting at each other all the time.
One thing that
And
really
an
comes, oh,
evolved
sorry. Okay.
universe, sorry,
Yeah, sorry, you
but
go.
an evolved universe just solves this problem. An evolved universe is meaningful. It's packed with meaning. It's directional, but it's not deterministic. It's because you have the bottom down causality of the fundamental particles, which is true. They are doing their thing. They are interacting in ways that are predictable. Essentially, I mean, quantum dynamics points out that they're not actually predictable. But okay, but there's a mathematical logic giving a bottom up causality. But there's a top down causality that we are generating that is also real. It's also true.
Yeah.
And you can see the reductionist materialists who don't understand there's other methods of accessing truth tie themselves into knots trying to explain that we don't really make decisions that have consequences because it's just particles. Well, yes, it's just particles, but when the particles self-assemble into highly complex reflexive systems that can model their environment, generate information about that environment, act on that information, you know, a particle-only theory does not explain why I punched that guy in the nose. Knowing that I think he's the guy that kissed my girlfriend when we were teenagers does explain why I punched him in the nose.
Yeah.
Is my model, is my information accurate? I don't know. We'll have to work that out. We'll have a conversation afterwards. Oh God, it's the wrong guy. I'm sorry. But you can't do a particle-only analysis of why I punched that guy in the nose.
Yeah.
There's top-down causality. He's in hospital, and it's not because particle movements.
Yeah.
It's because Information processing in a complex agent, in a complex system of systems, led to an action that couldn't be predicted by looking at the protons, no matter how closely you looked at all the protons.
Yeah. Yeah. This really
Yeah.
reminds me, I was stunned to learn that in ancient Egypt there was no word for religion. The
Oh,
idea that that
yeah.
aspect of life could be separated and put in a temple and kind of walled off,
Yeah, yeah,
it
yeah,
was
yeah.
conceptually impossible. And
That's
it's
interesting.
only really a way of thinking that comes during ages of rationalization, like we had
Yeah,
recently through the
yeah,
Enlightenment, that
yeah,
there's this split, there's this I, you
yeah,
couldn't really call it a schizophrenia, but there's this quarantining of ways of looking at the world in a
yeah,
complex society. And maybe it doesn't
yeah.
need to be that way forever.
It
Maybe
doesn't
there
have to be that
is,
way. Yeah,
yeah,
yeah.
there's a potential
It
for a
doesn't.
reunification of
That's what I'm
science
hoping for.
and what
Yeah,
we had called religion, which we'd pushed off
yeah,
into one
yeah.
corner.
Yeah, I think so. I think, and also we've pushed science into one corner. Like both of
Mm,
them are suffering. Both of
mm,
them are suffering here. Both of them don't have tools they need to understand reality.
mm,
I think, I mean, Ian McGilchrist's approach to this is a very useful metaphor, whether you think it's true or just a metaphor. It's a very useful approach. The idea that we have two modes of perception. He will simplify it into left hemisphere, right hemisphere. He will also acknowledge that's an oversimplification and there's a lot happening in both hemispheres. But that we have a perceptual system that takes in everything, and we have a perceptual system that abstracts out from that a simplification, a model that can then allow us to act.
mm.
Because you can't react to everything.
Yeah.
And that those two systems are required to full understand reality, and that we're overweighting the abstraction perceptual system, which is science. Science is abstracts and simplifies and reduces. And we've overemphasized that in our society. I mean, we've mathematicized the world. Like
Mm.
everything in this room is right angles. You know, everything in your room is right angles. We've mathematicized our environments.
Well,
Understandably, because otherwise things slide off the shelves. I
yeah.
mean, I get it. You know, there's a lot of benefits to it, but the world isn't right angles, and it can't be. There isn't a mathematical formula of everything that will explain everything. It's like another metaphor I'd like to use is that the people are people are looking for scientists are looking for a mathematical elegance to explain the universe, but the form of and they can't understand why all the basic parameters of matter are so they have these weird arbitrary values. Where's the elegance? They keep looking for the elegance, and they will come up with supersymmetry theories, where there's mirrors of all of these things, and that makes it symmetrical again, and therefore it's elegant. And that's a complete waste of time. That's not because the elegance of the universe is the elegance of a jaguar,
Mm.
right? The DNA of a jaguar is not elegant. It's full of little botches and workarounds and oh shit, we're out of the ocean now. We have to breathe air. Okay, let's turn our swim bladders into lungs. Okay, now we're a predator. Okay, we're gonna have to digest differently. Let's oh god. Oh, now we're climbing trees. Okay, I better get longer claws. It's full. The DNA is full of botches and workarounds, but the jaguar is elegant,
Mm.
right? This universe is elegant. The basic parameters of matter that generate this universe, they're not elegant. And they're looking for it in the wrong place. They're looking for the explanation in the wrong place.
Now, one thing I've also seen that really caught my attention was that and I hate to use the word religion because I think it means
Sure.
something specific and stunted in
Yeah.
our current sense of it. This is a more
Sure.
ancient, like
Yeah.
pre-Enlightenment sense of, I think it's just worldview or philosophy, or I don't know, it's an
Mm.
attempt to integrate everything in life. But
Yeah.
that really great religions need a mystery at their heart. And
Uh-huh.
I think this
Yeah.
is why this theory has potential because it's an explanation, but it isn't a conclusion. Like it's
No, it's not a
pointing in a
conclusion.
direction and says
Yeah.
we have reason to believe that this is possible,
Yeah.
but
Yeah.
it's also likely that it's not a guarantee that
Yeah.
our universe is on it's on its own journey and it needs to figure out if it can reach what we think is the next stage of its evolution.
Yeah. But the thing is, We are the universe.
Yeah, we're part of the
We
process.
we are part of the process, and we're aware of the universe. We're aware of the process. We're aware. We are the point where the universe wakes up and starts to move its limbs
Mm,
and starts to decide what it's going to do next. It's not we're sitting back from the universe going, I wonder what the universe will do next. We're doing it.
yeah.
And it really matters what we do next. Our choices have consequences for this entire biosphere. And this biosphere is a really it's an important part of the universe. It's let's not worry about all the other biospheres out there. We've got one, and we're like we're unfortunate. Well, no, we are as part of the developmental unfolding of our universe. One stage in that is intelligent life will at some point emerge, and it has emerged. It will some point be able to manipulate matter to the point where it can do things that couldn't possibly be done under a natural pre-life circumstance. We've
Mm,
hit that point. We are generating all kinds of chemicals and alloys that nature couldn't possibly produce on its own. And we are now entering a sort of biotechnological era where we are literally shaping the planet. The temperature of the planet is a consequence of our decisions and actions. Whether life is whether there will be life on the moon in 200 years or not, or whether there will be life on Mars, or whether there will be floating asteroid built, microbiospheres circling the Earth in 200 years' time, is entirely up to us.
mm, mm.
The actual physical development of the universe at a scale that you could bloody see with a telescope from outside the solar system is currently ours.
Mm.
We have to really think about this and not screw it up. But it's also very beautiful. The future of the universe is open. Is this going to be a lovely universe that's very friendly to life and that has where everyone has a great time, or is it going to be a horrendous, hellish, you know,
But
dystopia? We don't get to decide because the rest of the biosphere has also got some votes in this, but we get to negotiate that with the rest of the biosphere. We're part of this like extraordinary moment. It's amazing to be alive at this specific moment,
I would totally agree.
where we yeah,
Have you read The Unbearable Lightness of Being?
oh, a
The
long time ago.
now
Yeah, Kundra.
for the not many people
I
have.
mostly
It's
remember people
obscure.
floating up into the air in the square. I don't know. And there was some great sex, if I remember. Yeah.
Oh, are you mixing it up with 100 Years of Solitude?
No, I don't think so.
Okay. So
Doesn't he float into there's a crowd in the square, isn't there? Oh, I might be wrong. And they're sort of dancing, and then they sort of float up into the sky at some point
I know that happens in
in
100
Lightness
Years
of
of
Being.
Solitude with one of the
Does it? Oh,
yeah.
God, maybe
Anyway,
look, forget it.
the message I'm
I
taking
said
from
nothing.
Kundera
Yeah,
in his book,
yeah,
which is mostly just people doing things in like around the world wars in Eastern Europe, but
yeah.
his core idea is that the common perception is that life is difficult because it's heavy, that we have all of these burdens that we can't escape,
Mm,
and we have these duties and all this, you know,
okay, yeah, yeah.
but the reality is that life is difficult because it is light.
Ah,
Because if you think beyond those burdens and the potential failures, it's all relatively
yeah.
inconsequential. And I
Doesn't matter
wonder,
enough.
yeah, well, I wonder if
Yeah,
this theory, this cosmic natural selection, takes some of this burden. And I would refer to
yeah,
Elon Musk saying we have to, ASAP put a colony on Mars, no matter how
yeah,
horrible,
yeah,
no matter how
yeah, yeah,
expensive, whatever the cost,
yeah,
as a backup,
yeah,
because we're the only complex,
yeah, yeah,
intelligent life. And if we don't get it
yeah,
right, it's all
yeah,
for nothing.
yeah.
And if you have this wider, more evolutionary perspective, we're probably not the only complex life that's going to appear in our
Oh, it's
galaxy.
gonna be everywhere.
And
Right, yeah, yeah, that's everywhere.
our whole
Yeah.
universe isn't the only attempt. So
Mm.
it gives us
No,
freedom to try our
yeah.
best, but not
Try our
this
best.
awful
Yeah.
sense of
Oh, yeah,
of
yeah, yeah.
responsibility that it's all
Yeah,
on
yeah, yeah,
us.
yeah. Yeah, yeah, yeah,
I think that's a more
yeah.
productive way for us to explore what is possible
I think we should
than
do it playfully. I think we
yeah.
should not get crushed by the scale of it. Yeah, we should be doing it playfully. Yeah. We'll give it a go. We'll give it a go.
And we
Or
have like
yeah.
tens of millions of years of habitability on Earth, give or take, the odd asteroid that's going to come and shake
Yeah,
things
yeah.
up. But I
Well,
mean, mice
we're
and
gonna be
birds
able to
made it
spot
through the
those soon.
last really bad one of
Yeah, true.
those. We'll be fine. We'll figure it
We'll be
out.
fine. Yeah, yeah, yeah. Yeah. No,
Um,
I think it's very hopeful. I think it's very optimistic. I think it's great. I think it's great to be alive. It's great to be human. It's great to be on this planet in this biosphere at this moment when everything's changing. Of course, it's terrifying, and of course, we have this sense of apocalypse because, we have kind of lost control of the temperature a little bit. And actually, my feelings about that is if life is going to be common on planets and moons, there should be a sort of something like hydrocarbons, a huge store of hydrocarbons as the yolk sac, as the way of feeding the life form as it gets intelligent and starts to try and manipulate the environment
mm,
would make sense. But then you should move on to something like fission, which is far more intelligent, like far more you know less destructive of the overall biosphere and more efficient. And we didn't do that. I think we panicked ourselves after Hiroshima and Nagasaki, and we freaked out about nuclear power when we should actually have transitioned to nuclear power. And the consequence of that is we are overheating the environment because we're burning more of the hydrocarbons, I think, than is probably optimum
mm, 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 mm.
if we're going to be moving forward into more and more efficient energy production. So it's interesting that we might have glitched our own development there, Mm.
How far out do you think technological small black holes could be? Like if
I
the
think they're pretty far
sun,
out, man.
yeah, if the sun is
Uh,
fusion at a safe distance, then
yeah.
where would you put one of these black holes so it didn't accidentally get away from
Oh, I
you?
think, yeah, I think it's something you would probably do to asteroids on asteroids. You
Mm.
don't really want them falling to the center of your planet, messing it up. I think you put them in space. I think you have them, uh, and then you microwave or you send the energy to where it's needed. But I don't think you want them on Earth.
Mm, mhm,
I think
mhm.
they're real. They're what the asteroids are for. Yeah.
Now, what
I
else?
didn't. I realize I haven't actually filled out the last little bit of blowtorch theory.
Oh,
The
yes,
thing I recently put up a month ago,
on
which
your
is
Substack.
on my Substack, which is
Yes.
I think it also explains this theory explains structure formation in the early universe. So I was telling you, supermassive black holes generate the galaxies around themselves, shock the gas, nucleate out star formation. But I think the jets can. We now know that from 6 months ago. I think we discovered jets that are even longer than we had thought were theoretically possible, and earlier than we thought were theoretically possible. And my argument is that the jets in the very early, extremely dense universe, because I don't think people understand how small and dense the universe is at redshift, 20, 30, 40. Like if you go back to, you know, 50 million years after the Big Bang, or whatever, or 20, 30, 40, 50, 60, 70 million years, the universe is thousands of times smaller in volume, because it drops with the cube of the size. So if it
Mm.
gets 10 times smaller, it gets
A thousand
100,
times more
1,000 times
compact.
more dense.
Yeah. Yeah.
So it's unbelievably dense. So the jets can be very sustained. They get a lot of fuel and they can shoot huge distances. That as the universe expands, uh, any any structure formation that's done at that early stage becomes enormous in our current universe. So I think we know that jets form cavities. They blast out low pressure. They create these huge cavities, pushing the gas out from the north and south poles of the galaxies that the jets come from. We know that happens, and we know that the jets are electromagnetic, tight electromagnetic, jets
Mm.
channels. Uh, in our current universe, we have 80% of the universe is voids, which have almost no stars or gases in them. They're more than 10 times less dense than the surrounding material. And we have filaments which connect the places where the galaxies kind of cluster together. And those filaments contain gas and galaxies and are much, much denser in gas and galaxies than the voids. And the structure formation explanation for that currently is not very satisfactory. Again, lots and lots of dark matter and whatever. My argument is that the jets are going to make cavities that are early enough and these are going to be big enough and early enough that they later expand to form the voids. And the paths of the jets, the electromagnetic paths of the jets, form the filaments. They bend over time over the kinetics of the expansion of the universe. They expand, they merge because the electromagnetic they're going to connect with other filaments, and you're going to get uh, a structure that is actually carved actively by the very early supermassive black holes and their galaxies, rather than passively assembled slowly by gravity alone.
Mm.
And I've made about 10 solid predictions. There's stuff we should be able to see if that's the case. You should have probably a helical electromagnetic field in the filaments, because the jets have helical magnetic fields because they're coming out of spinning black holes. So there's a spin to their electromagnetic fields, which
Mm.
actually helps stabilize them, by the way. And that means that also there should be less turbulence in the gas moving along the filaments.
Mm.
That is actually something we're sort of half seeing. It looks like it's not as turbulent as it should be. My explanation is you're going to have helical magnetic fields from their production by the jets that allows them to be less turbulent. It allows for laminar flow.
Mm.
So anyway, that's the last bit of blowtorch theory. Yeah, yeah.
And do you have
Actively,
any?
the universe actively forms itself from the start, which is what you would expect in an embryo lays down its later structure
Yeah,
as early as possible while it's still cheap and easy to do. I'm
yeah,
saying the universe does that.
yeah,
Yeah.
yeah. Do you have any hints on where you think you're going to take the theory next?
Ooh.
Or do you
Uh,
not want to give it away? No spoilers.
no, no, it's not that I want. Well, I think what I'm working on, the next big thing I'm working on is I'm trying to explain galaxy rotation. I'm trying to apply this theory to galaxy rotation because that's a big problem that we have been solving with dark matter. If I'm right and there's just less or no dark matter, uh, I have to explain gravity rotation. I have to explain galactic lensing. There's a few things that, the current theory, there's a reason why it's there. If you fudge the parameters enough, you can kind of explain about 5 different phenomena. I'm going to have to explain them all separately
Mm.
if I'm going to, unseat the current paradigm, which is fine. I like the challenge. So I'm working on galaxy rotation, and I do think there's a model there for modeling the galaxies as taking more seriously the electromagnetic bubbles that surround every star, the astrospheres that are generated by the solar wind, because there's an electromagnetic bubble around every star. They generate them. Why do they generate them? That doesn't make sense in a asking why they generate them doesn't make sense in a random universe paradigm, but it
Mm.
does make sense in an evolutionary one. They're putting a lot of energy into it. The solar wind, that's a lot of energy to generate this electromagnetic bubble, which, by the way, protects us from cosmic rays. It has protective. We've got two layers of protection around us, protecting us from high energy particles, fucking us up. We've got the sun's heliosphere, and we've got the Earth's
Magnetosphere. Yeah.
magnetosphere. Yeah.
Yeah. I'm not going to
So
Mars in a hurry.
yeah, that's a lot of radiation on the surface there. Yeah, but where's it going next? I don't know. What's happening now is I want to talk to more scientists. So if anyone wants to get in touch that has ideas on this, I'm talking to some astronomers that are working on a really interesting telescope that might be able to image some of the stuff I've predicted in the filaments, because they're low brightness. It's hard to see the gas in the filaments. This telescope can do that. So we're having a really interesting conversation at the moment about how to do that. So what we're moving towards is trying to find more evidence for the theory, but also extend the theory into other areas. It's crazy that I'm probably the only guy on Earth who's working on this full time. It's just bananas. It's so underexplored. This theory is so underexplored. There's just like, we need a lot more science. So I'm going to probably move to the Bay Area later this year and put together a working group, an evolutionary cosmology working group, and get some scientists from other fields to kind of uh, just talk these things through, work out new research areas, and then they can go back to their institutions and pursue research in their different fields that might be useful. Because we really need a lot more people working on this problem. It's ludicrous that someone like me gets to play with it all on his own. It's been great fun, but I really need to hand it over to some people and have the experts play
Well,
with it for a while.
a related question. Do you think our society is getting better or worse at paradigm shifts?
Mm, that's a very good question. I think structurally we're getting worse because I think what we've seen in the last century is every single science has gone through a kind of phase transition from from this kind of plucky startup energy where you just have quite a small number of people working on these problems and very intensely, and they're not that constrained by convention because there isn't a convention yet.
And
There isn't.
they're structurally allowed to take risks without their career just being fitzed out.
yeah. You can take risks. A field where there's only 100 PhDs in the entire field in the world is very free.
Mm,
You can just do your nutty thing. There isn't a consensus because there aren't enough people. There isn't a sort of but a field where there's like 500,000 PhDs in that field and they're fighting for these various positions and it becomes about the status games of
mm,
the corporation. Corporations are just slower than startups and they're much less open to innovation. And what's happened is a psychological movement from startup energy to corporate uh, bureaucratic caution across every science. All the sciences are basically too big,
mm,
and they don't have a sociological model that allows for disruption. So what they have is this, there's this, they've got this kind of equilibrium paradigm, and anything that disturbs the equilibrium of the paradigm is seen as bad.
mm,
And some of the things that disturb the paradigm are errors and mistakes and should be, it's good that they, don't smash up the paradigm. But some of them are the breakthroughs that will replace the paradigm, and they get squashed exactly the same.
mm,
So there's no mechanism to tell the difference. And peer review is brilliant in many ways, but it's brilliant at getting rid of the bad papers.
mm,
The trouble is, it's also brilliant at getting rid of the unbelievably brilliant papers that have stepped outside the paradigm. There's a lot less of them, so you don't notice that this is happening. But you've got a bureaucratic, enormous corporate structure now for all the sciences with no disruptive mechanism and a peer review process that filters out all the bad ideas and some of the best ideas. And I think it's made it very difficult to do paradigm shifts. Where is the point of leverage for the paradigm shift? When Einstein came along, he could literally talk to everybody important in his field, write them personal letters, and
mm.
convince them. What would he do today? If he
Yeah,
was in
yeah.
the patent office today, if there's a physicist who's just as bright as Einstein and it comes up with an idea that's just as revolutionary as Einstein and is working in exactly the same place, in the Swiss patent office because he can't get a university job, what is his point of leverage?
Yeah.
He has none. He has none. So what you end up having to do is you have to go outside the system and talk to, what you have to do is find nodes of influence in networks outside the system that will eventually feed back into the system.
Yeah,
So you
yeah.
need really good podcast hosts are useful. There's people like Kurt, who does that Theories of Everything
Joe Mungle,
podcast, and
yeah,
there's people
yeah.
like, yeah, and there's people like Dwarkesh Patel does a very
Hmm.
good pod. There's some podcast hosts who are respectable enough but open-minded enough to push a new theory into the conversation.
Hmm.
That's one way of doing it. People like Tyler Cowen, who's funded my work. I targeted Tyler because I thought he's a node in a network. Uh, he has a great bullshit filter, but he has a very good reputation for finding undiscovered talent.
Mm.
If I can convince him I'm right, that will convince a lot of other people, and that's been the case. Having it have if you can persuade. So there are nodes in networks, but they're now outside the mainstream academia. The networks you
Mm.
need to persuade are outside that, and then you hope that the pressure from the outside will force the people on the inside to
Catch up.
reconsider.
Yeah.
It's very difficult. Paradigm shift is now very difficult, but it was always kind of difficult, Yeah, yeah.
It makes me wonder if the leading edge of this theory could actually be its cultural impact. If you convince ordinary
Mm,
people
yeah,
that it resonates with them, that will create. I mean, politics is
yeah.
downstream from culture, and if modern academia is mostly politics, then
It
maybe
is
that's the
now.
same pressure point.
Yeah, I think I think there's going to be an unavoidably a huge amount of resistance. No one psychologically wants to think I wasted my life up to this point on a paradigm that isn't right. Huge numbers of people have poured their lives into projects that are going to look really silly if this paradigm shift happens. And I have enormous sympathy for them. I actually don't know. I do think more and more about how do I communicate with people when what I'm saying to them, then they're not going to want to hear it. It might be good for them long term. It's going to be horrible for them short term.
Mm.
If you've spent your whole life on a dark matter project that there's nothing there, oh God, and you've got to do a career shift into a new subfield
Learn a whole
in
lot
your
of new
40s or
mathematics.
something.
Yeah.
Just
It's
not going to want to do it. And you're going to have to learn a lot of the evolutionary theory that is just, that you aren't interested in. You moved into this field because it's pure math, and now it turns out to be about weird, squishy stuff like the biological kind of processes that that's what they went there to avoid. So it's going to be very, very difficult. I think what's going to actually happen is we're going to generate a new field
yeah.
outside the existing. I don't think you can convert the current. You can't convert a research group that have just spent all their life under a mountain in Italy looking for dark matter particles in
Giant
chilled
photo multiplier lab tanks.
yeah,
Yeah. You know.
they're not going to be interested in the kind of stuff we've just been talking about. It's
Yeah.
just not their thing. So I, when I like the Bay Area, I will set up this evolutionary cosmology working group, and we do actually have a long-term plan that will form the basis for a more long-term evolutionary cosmology institute that will have people from multiple fields. You have to generate a fresh field from scratch here. There's literally nobody out there who's qualified to do this. There are people who have fantastic, deep knowledge of an incredibly small area
Mm.
of evolutionary cosmology.
You need to find
And
the
some
right
people
people
have
to join them
broader,
up.
you have to
Yeah.
find the right people to join them up. But there's people like, Robert Hazen, like that mineral evolution stuff I was talking about,
Mm.
that comes from Robert Hazen at a party where someone asked him, where does this particular shale come from? And he didn't, how old is it? When did it first appear in the historical record? And he didn't know. And he realized that nobody in his field knew how old any mineral was, like
Yeah.
when they had first occurred. And he was like, whoa.
Let's put
And
this all
he put together
together.
a
Yeah.
team. He put
Yeah.
together a team and they spent a year or two and they worked out when every single mineral appeared for the first time on Earth. The pattern when you see it is one of explosive complexification. It's beautiful to see.
Mm.
No one had done it before. And
Mm.
that's going to have to happen in every field.
Yeah. 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 Yeah.
Yeah.
I have one other
It's going
kind
to be
of
beautiful. It's going to be so disruptive and generative of new ideas. It's going to
well,
be beautiful.
a parallel could have been it could be Darwin's theory of evolution, how that upended biology. It gave it
It's
an
going to be the same thing
entire new
for everything,
lens.
for
Yeah.
everything. Yeah.
But
It's going to be exactly very similar. Yeah.
I had
Go on.
one kind of fun question, but maybe kind of dark as well too. Do you
Mm.
anticipate the the popular imagination running away with this solid enough theory and then applying it to every kind of, you know, paranormal, kooky, metaphysical,
Yeah.
spiritual
Yeah.
experience to use it as a lens? I mean, it's kind of harmless, but maybe not in the early stages when you're trying to establish credibility.
You will notice that all I have talked about in this entire thing is just I'm talking about a scientifically plausible explanation for material reality.
Yeah,
I'm not going outside of that. That's all I can do for now. I totally understand that as soon as you bring consciousness into this story, as soon as you bring you can go very, very woo-woo very, very fast with this theory,
exactly.
but I don't want
Exactly.
to do that.
No.
I want to convince the existing scientific mainstream that this is a scientifically respectable mainstream way of thinking about the universe. But I also understand that the mystics are going to
They're
find
gonna
this
love
really,
it.
really
Yeah.
interesting and are going to play with it. And they should be allowed. They're totally allowed to play
Have
with it.
fun with
Everyone's
it.
allowed to
Yeah.
play with it.
Do,
Everyone's allowed to
do
play with
you
it.
know what
But
you
I
almost
can't do
need?
that right now
No,
because
no, 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 no.
it will cripple the theory.
I know, but do you
Yeah.
know what I would almost anticipate being advantageous?
Yeah.
To actually
Yeah.
have a team of artistic physicists or whatever to create memes and works of art that poison the well, that actually take it
No, I don't
too.
want to.
No, 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 that take these ideas to the point that they're ridiculous so that they're not entertained in the middle, kind of murky, semi-serious ground, that it's something
Well,
fun that you can play around with, but
I don't want
it's
to over
already
control
framed.
this.
Well,
I don't want to
yeah,
over control this.
I don't think
I
you
think
need to, but it's
it's
just
going to go
interesting
nuts.
theorizing.
I
Yeah.
think once the idea that the universe evolved,
Mm,
that it's going along a developmental path, that we're part of that developmental path, we're the point where we're the growing tip of the organism,
mm,
uh, and that it's a meaningful environment.
mm.
It's going to be explosively psychologically transformative, and some of the effects will be negative.
Mm.
But some of them will be positive, and I don't know in advance. I don't want to try and over control how that plays out. We're going to end up in a massive meme wars. Yeah, yeah, yeah. I mean,
Mm.
I'm actually I do think about it in meme terms sometimes because like that's why I say biology is the first half of the periodic table coming to life. Technology is the second half of the periodic table coming to life. Because that was a process of deliberately trying to think. There's this very complicated thing happens over 3 generations of stars inside an organism that's membrane bound that develops out the elements to form this three-stage reproductive. How do you put it on a t-shirt? How do you? And it's like really like how do you put it on a t-shirt? Because if you can't get the essence across in it's obviously it's more complicated than that, but you need to get the
You need
essence
like the
across.
ascent of man, but for the cosmos.
Yeah, 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 yeah. Yeah. So
L-
I'm
Yeah.
thinking about the meme side of it.
Let, let,
Memes will be very important in this because most people are not going to read my blowtorch theory post. It's
no.
14,000 words long and it's really dense.
Mm.
The Irish Times ran an article on it yesterday, and that was great. It was 1,200 words, and it got a lot of the essence of it across. But most people aren't even going to read the Irish Times article; they're going to read the T-shirt. And you want to have a funnel where people can get to the blowtorch theory post and read the 14,000 words, but
Step by step, yeah.
you get them there through the T-shirt. That gets them to the article. That gets them to the post.
Yeah. I mean,
Yeah.
that was the advantage
Because
of
Smolin didn't do the
evolution.
T-shirt.
Theory of
Sorry.
evolution had that advantage of like once you see chimpanzees in that light, it
Can't unsee it.
recontextualizes not just your
Yeah.
life, but your connection to everything, and you can't
Yeah.
unsee it.
Can't
And
unsee it.
it,
I think
it's
this is
it.
similar. I think
Mm,
this clicks with people. I've talked to a lot of people where they read they read some of my stuff, and at some point they went, "Whoa!" and
yeah,
they can't unsee it.
yeah.
It's a developmental process. It's look at it. Just look at it. Hot gas. Hot gas. That's all it is. There aren't even atoms.
Mm,
And that becomes atoms, very simple atoms.
mm,
And those simple atoms become slightly more complicated atoms. And those slightly more, and in my argument, collapse, form supermassive black holes. Supermassive black holes generate stars. Stars generate more stars, generate more stars, distribute elements in a really complex way, distribute elements. There's a complex circulatory system going on there.
mm,
The part of blowtorch theory is explaining in evolutionary terms why you have filaments. Why are the
mm,
filaments attached to the clusters of galaxies? The filaments are feeding reservoirs of gas that have been stored by the early structure formation, feeding reservoirs of gas back into the galaxy so that as the supernovas explode, there is fresh hydrogen gas to enrich to make the next round of stars,
yeah,
and thus the
yeah,
planets, and thus the life. It's
yeah,
a complex circulatory system. You cannot unsee it once you've seen it.
yeah, 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 yeah.
Yeah.
And that is why I am so grateful that I got a chance to talk to you. Not just for my usual hour. I've lost all track of how long
Oh,
we've been here.
sorry. Yeah.
That
Oh, wow.
no, no, no.
We've been
But
here a
we have been
while.
having so much fun, and
Yeah. Yeah. Yeah.
I was very lucky to get to ask all of my slightly fringe questions, but hopefully
No,
respectful.
I love it. I love it. No, I love just the fact that people are engaging with this is so wonderful. I spent about 10 years thinking about this on my own before I thought to look up and put ideas out in the world. And then when the James Webb was coming on, I thought I really have to start talking. I have to make predictions. I have to go into public now. I have to talk to people about this. It's
Yeah,
not, and it's not my natural, no, no, where is it my natural mode? I don't know. I was in a very kind of hide in my room, think, read, research, go nuts on my own kind of,
mm,
check against reality now and again, but go nuts on my own period for a long time. And now it's lovely to be sharing these ideas with people who have really interesting questions, who want to take it somewhere, who can contribute to it. It's just
mm.
just a delight, delight. I'm having
And
such fun.
And if you ever have a really long flight and don't want to
Yeah.
read scientific papers, I can send you a copy of Our Vitreous Womb. It's mostly about
Do
biological evolution, a different
yeah,
path
yeah.
of post-technological biological civilization on Earth. It's a
Right,
hard
right, right.
sci-fi, but it has this thread of cosmic natural selection in the background
Yeah,
as
yeah, yeah.
a religion that these people believe in, with just little hints of woo. You always drop in
I'm okay with
put
hints
it,
of woo.
yeah, you put a drop of woo in.
The universe is full of hints of woo.
Yeah.
So yeah, no, I yeah, no, send it on. Yeah,
Mm,
the fact that you're thinking about the the post-technological, biotechnological future and where that goes and what people believe is really good because you will help shape that future. People
Yeah.
will read, science fiction shapes the future. The reason Star Trek, look, the reason we have mobile phones that are like they are is because someone wrote them into Star Trek when they were completely impossible. And the first Motorola clamshells were based on the communicators in Star Trek.
Mm, mm.
It's
And
a feedback loop.
I definitely think that sci-fi is overdue for a paradigm shift as well, that we're
Yeah,
kind of
yeah.
stuck in, late
Doom sci.
1800s to 1950s visions, and they've gotten a little
Yeah,
bit stale and a little bit
yeah.
overprotected, and it's time to
I
shake
loved,
things up.
yeah, I loved science fiction growing up, and it was the thing I read by far the most of. And then I kind of it went away from me, or I went away from it, and I'm not sure which. Yeah, there's some
Mm.
good stuff, but it doesn't feel as exciting as science fiction used to feel. Used to feel.
It used to
Partly
be
that's because
really risky. It used to take
yeah,
chances, and I
risky.
think it's
Yeah,
parallel to what's happened with research itself, that the dynamics of
yeah,
the whole culture
yeah.
has kind of stagnated, and it's time to
There has
stir
been
it
a lot
up a
of
little bit.
stagnation.
Let's
Yeah. Well,
compact it down to a singularity and explode it again.
well, one thing I think that's going to happen with this is it forces the borders of the sciences to move. They're in the wrong
Mm,
place to understand this.
hmm.
And if you shift the borders of the sciences, I think there'll be an explosion of innovation because loads of people are working right next door to a scientist in a different field who has a great idea that would be of enormous benefit to this guy here, but they don't talk the same language. They haven't really com communicated properly for 50 years because they've
They've
diverged.
diverged.
They've speciated, and now you're going to get this. I think you're going to get this Precambrian explosion of remixing of all of the sciences because you have to integrate all the sciences to understand an evolved universe undergoing a developmental path. It's really transformative,
Th
and
th
that will be, I think, wonderful for innovation.
this is possibly my last idea that I'll throw at you out of left
Yeah.
field. So there's hints that the physical constants of the universe drift as it
Mm,
evolves.
yeah.
And I mean, it's one of these other fringe physics theories. If that's
Yeah.
true, and cosmic natural selection is true, and black
Mm,
hole mergers are true, could black holes that
mhm.
are at different stages in their developmental process merging create hybrid universes that can do something that individual universes couldn't do previously? It's a mechanism for evolution.
Oh man, I love that you're asking this question.
I'm like
I
10
love that you're
steps
thinking
ahead.
these thoughts.
This is how my mind works.
I I don't have I do think it's very interesting to ask if if this is true, if this theory is actually correct, what are black hole mergers? What happens to the
Mm.
universes? It's really, really interesting, but I don't have an answer. I'm
Put it on a
fascinated by the
t-shirt
question,
for
but
me
I
right
don't have an
now.
answer.
Put it on a t-shirt for me right now.
Well, it's very interesting. I don't know. I don't know. I don't know.
Mm.
Yeah.
Because
Yeah.
that's my theory that I'm
There's so
coming
much
to.
work to do.
Yeah. Well,
Yeah,
this
yeah,
is my
yeah.
advice coming at you from somebody who's reading a lot of wide fringe biology, that
Yeah. Yeah, yeah.
hybridization seems to be
Hybridization, yeah.
one of the key drivers of diversification in
Mm,
biology. And I'm applying that
very
lens to
interesting.
cosmic natural selection. It's like, where is that creeping
Can
in?
you hybridize
Because
universes?
Darwin's little
My toy.
branching
Yeah.
tree is,
Yeah,
it was
yeah.
a lovely first step, but it's when
Yeah,
those
yeah, yeah.
branches cross back over where the real
Yeah,
fun
yeah, yeah.
happens. And I suspect it might be
That's
true.
intriguing.
Yeah, I think it
Yeah.
might be true for
I
cosmic natural selection too.
Well, I am being deliberately so frugal in my
Mm.
the model I'm using is like so simple. I'm just saying because
Oh, you've got your work
I
cut
and
out for
I
you. I
yeah,
don't
it's just
resent you
the
of
thing
that
is
a second.
I think you're correct that the actual version of the theory we're going to end up with is going to be much more complex than the simple toy version I'm giving us.
Mm.
But I don't know which of those many alternative versions
Yeah,
of it are going to be true. What I want to do is get a sort of a basic toy version, like as Darwin did with
exactly.
Origin of Species,
Yeah.
and say these are the simplest possible rules for the simplest possible version of it that I can think of. As you encounter oddities and complexities, you will complexify this theory.
Yeah.
But I can't jump to the finished version because I'll lose everybody. if I add two more layers of speculation to this, I lose everybody. Or I gain the kind of people that love being speculate, love speculation right out on the fringe. But I'm not
You
trying to
lose
speculate
everyone
out on the
else.
fringe.
Yeah. Yeah. Yeah.
I
Yeah.
lose
Yeah.
everyone
Yeah.
else. Yeah.
Yeah.
But go forth, young man, and conquer.
As
Yeah,
long as
like
I don't
totally,
expect
totally play
anyone
with
to
it.
follow me in a hurry. This is just how
No,
my
no,
mind works. Yeah.
no. Let a thousand flowers bloom. There should be lots of different people working on this. This should be this should be
It should be
an
fun.
explosion of diversity.
Yeah.
You might be you might be the guy who has the big insight that blows it wide open.
Mm,
Everybody should be playing with this. I want everyone to play with this. This is fun.
mm,
Yeah,
mm.
yeah, yeah.
And I hope this isn't like, what would you call it? Ass kissing. But I wonder what it would have been like to interview Darwin, like during the early stage of him working on things. Like he would have
Dar
been seen as a
Darwin
bit
was
of.
more original. Darwin was more original. I'm building
I
on
mean,
Smolin's work,
he
Clement
stopped
McDowell's work,
he
John
let
Smith,
he leapfrogged
Priya.
off other
Yeah,
people's work before him that didn't
yeah,
get as much credit. So I
yeah,
think
yeah.
history is repeating there as well too, and I'm really. I'm really hopeful seeing you taking the lead on this because I think you've got the right combination of skills to be a communicator and an investigator. That's a really rare combo, and you've come along at just the right time.
Well, that's lovely to hear. That's really, really nice to hear. I mean, I love this so much. I'm enjoying it so much. I think I have a very weird skill set that happens to be good for this problem.
Hmm.
So, but that's just, you know, luck and chance in many ways. But yeah, I think this is I think it's the biggest, most neglect it's the most neglected big idea, I think,
Mm,
that we've of the last 50 years. I think it's been neglected for purely sociological reasons. There are no good scientific reasons why this got almost no resources, and something like lambda cold dark matter got the or string theory or whatever. There are lots of speculative theories out there that got colossal resources over decades. And this got nothing. It got nothing. And I think that's a shocking um, mistake that was
mm,
made. And I want to help rectify it, you know. And
mm,
again, there's no bad guys. It's not that there was a conspiracy against this brilliant theory. There was a theory that was an orphan. The guy that thought it up didn't want to develop it because he had another job. The guys that there were no people qualified to go with it. It was just sat there neglected for so long because of just the way science happens to be structured around
mm,
an old paradigm. And this was such a different paradigm that there was nothing in place to support it. This is actually the difference with Darwin and Smolin, by the way. The Darwin brought a new field into existence that was dying to come into existence.
mm,
Everybody knew there was something missing.
mm,
And there was, when he came, there was no field of biology to be disrupted. There
mm.
was just natural science.
Yeah.
There was just natural
It
science.
was just stamp collecting.
It's just stamp collecting and just let's put funny names on these things.
Mm,
They were putting funny names on their stamp collection. That was it.
mm,
So he had this beautiful open territory and he could put new buildings in this open field and everybody wanted to help him build the new buildings,
mm,
right? Not everybody, because it was a battle, but nonetheless, you can see that there was he wasn't dis he had an open space to play in, and Smolin came along with essentially a Darwinian theory for cosmology, but cosmology was already fully developed
mm,
and in place and had a theory and was going and it was going to be very annoying for everyone to have to start again and do a new PhD to actually get up to speed to follow this theory. And so it just the seed had no soil to grow in. It had
What,
already been concreted over.
when do you
That's what
think
happened.
cosmic natural selection, the ideal time in history, would have been for it to be
Mm.
like back in Hubble's?
Darwin, Darwin. The problem was Darwin lived in an infinite, eternal universe.
Yeah.
He assumed the universe was infinite and eternal, and all the evolution that was going to happen inside this unexamined, infinite, eternal universe.
Mm.
So it was going to be animals evolving inside this single, eternal, infinite universe.
Even at
And
Hubble's
if
time,
he'd
it wouldn't have
known,
quite worked. Like even when
well, You need
I
the
don't know.
Big Bang. You need the
Yeah,
Big Bang.
yeah,
See, the problem was that if Darwin had known that our universe was was recently born and expanded in a membrane and developed
yeah,
over that extremely short period of time, he would have said, "Oh, it evolved."
yeah, yeah.
He would have said it. It would have been Darwin would have cracked this had he known about the Big Bang.
Mm, interesting.
Yeah,
I think we're going to
but
have
you
to
need the
wrap it
Big
up
Bang.
there. We've got
Yeah.
to wrap it up.
Okay, let's
I'm
go.
gonna be here
Yeah.
until midnight, and I'm gonna love every minute of it. But my poor listeners, they're
I'm
gonna be
sorry.
they're gonna be shriveled. Well, most of the people I think who, like me, spend their day out in the garden listening to podcasts. It's like this amazing new medium that you get to
Yeah,
hear the
it's great. I
voices of
love
all
podcasts.
sorts of extraordinary people for like
Yeah.
the hours of the day that you're doing something, kind of routine and mundane. So, and I'm very, very
Well,
grateful to have a chance to
I
bring
hope
your
I
voice to my
helped.
audience.
I hope I made the washing up more interesting for some people. Yeah.
Well, I
Yeah.
mean, it
But they
changed.
should join in too.
Yeah.
If they've got ideas, like you can tell them where I post my stuff and they
Yes.
can,
Yeah, yeah,
come.
yeah. So that's the final thing.
Um,
Where can people learn more about what you're doing and get in touch? So there's the Substack,
I've got a
the Rock
Substack.
and the
I've got a
Egg,
website called the egg and the rock
the Egg and the Rock.
com. The
Yeah.
egg and the rock.com. It's just one word, the
I'll
egg and
put
the
all the
rock.com.
links in so people can find them easily.
Yeah,
Yes.
yeah, because it's comparing the paradigm. Is the universe does the universe behave like an egg or a rock? Does it
Mm.
develop like an egg into complexity, or does it simply just slowly lose order like a rock? Clearly, I think it develops like an egg. So the egg and the rock.
Now you got me thinking
And
about
come and
cosmic
comment. I put up
chickens.
posts there. You can subscribe, and I'll send you all my ideas
Yeah.
as I come up with them, and get involved. Like I'm putting together. Like, I'm constantly talking to new scientists from different areas now about and they can bring really interesting new ideas to this. That's what I want to do. That's what I want to do. I want to just be a node in a network and build out the network.
Mm.
So,
Mm.
join in. This is this vast unexplored continent. Like it needs explorers. It needs
Mm.
you. Yeah. And your listeners sound like the kind of people who have the kind of approach to our universe that could maybe, bring something to this conversation.
Mm. Mm. No, brilliant, brilliant. And yeah, I'll wrap it off here. Otherwise, we'll start up
Yeah.
again. I
I'll let you
just know
go.
it. I know it. I know it. But
Yeah.
yes,
Yeah.
thank you, Julian, so much for taking so
Thanks,
much
Shane.
time to have this amazing conversation. I couldn't have
Yeah.
imagined that it would evolve in so many different directions. I shouldn't have seen it coming.
Well, it's hybrid vigor. Yeah, you and me together, Shane. Hybrid vigor.
Brilliant,
Yeah,
brilliant.
thanks for being so engaged and interested and thanks for I love talking about these things. It's very useful to get these questions and I think, yeah, what about that? It's very enriching for me as well. So thanks very much, Shane, and good luck
Excellent.
with everything. We'll talk again.
The Zero Input Agriculture podcast is a solo passion project built with my ample time and meagre resources. If you would like to support the show, then sign up for a paid subscription to my Zero Input Agriculture blog at Substack. As a reward, you can read all my past posts and listen to the audiobook of Taming the Apocalypse. If you prefer reading about the past and future of biological technology, you can read the ebook of Taming the Apocalypse through Amazon. And finally, please rate and review the show on whatever podcast app you use, since it helps other people find me. Or recommend the show directly to anyone who could use some inspiration to become a plant breeder themselves.